All right. Let's do boot.dev. Here we go. Okay, let me check my sound as I usually do. I think it's fine. Yep, that's fine. Okay, let's jump into it. Here we go. Enter course. I don't know how long this is going to be. Should we look at this? TJ, uh, do you say this? DeVries? Anyway, let's just jump in here. Welcome to Memory Management. Understanding how your software runs on hardware is important for writing fast, performant code. In this course, we'll be talking all about one of the main aspects of software performance, memory management. All right, the goals of this course. I'm not going to play the video. Goals of this course. Understand how and where programs store data in memory. Variables, functions, and objects don't get to exist for free. Where do they live as your code runs? Okay, we'll find out. 2. Learn how to make programs more efficient. Most performance-related problems in backend software are memory-related, at least in my experience. Okay. Learn how it all works so you can troubleshoot and optimize. Practice programming in a lower-level language. C gets you much closer to the hardware than Python, JavaScript, or Go. By writing C, you'll learn a lot about you'll learn a lot about how software works closer to the metal. And 4, learn about garbage collection and build your own. You will likely work in a garbage collected language at some point, whether that's Python, Go, JavaScript, or something else. Best to understand what trade-offs are being made. Note, this is not a C course. We will be writing C code and we'll cover the basics of C that you'll need, but we're focusing on memory, not C. Prerequisites, coding experience. You should be comfortable writing code in at least one other language, like Python, JavaScript, or Go. CS basics. We expect that you understand basic algorithms, data structures, OOP, and FP concepts. Okay, so if we look, what do we do here? So the course is listed as number 12 after having covered all those things. Okay, that's fine. So, building snakelang. If you're familiar with super high level languages, you're probably used to not thinking about memory. In this case, we'll be building the snakelang programming language. Okay, just little parts of it. In a C, we will study all about manually managing memory in C, and toward the end of the course, we'll build a simple garbage collector so that snakelang devs don't have to think too hard. A small bit of irony here is that C was originally considered a high-level language when it was released. Ah, yeah, because that was a long time ago. And in fact, in some ways, it still is. Modern compilers and hardware are incredibly cool and make impressive optimizations. But even so, I think there is a lot we can learn together on our snakelang journey. Yay! Assignment. The ultimate crime has been committed. Someone's confused Python with snakelang. Update the code to print starting the snakelang interpreter. Make sure to keep the new line character at the end of the print statement. Okay, so we'll just do this here, and let me make sure okay, starting. Okay, so that's fine. So we hit that, but you know, I didn't hit a potion first. Let's just hit a potion right now. Potion, activate. Okay, 30 minutes. Let's go to the next. C program structure. In Python, you'd do something like this. Python slow program py. Okay. The Python interpreter then executes that file top to bottom. If you have a print at the top level, then it will print something. Okay, cool. The entire file is interpreted line by line, but that's not how C works. Ran out of battery again, but I have some more, because I think I've been using batteries that were almost dead. Battery in my mouse. These batteries should be fresh. I think how many do I have there? I put 5 different batteries in there. I think they all must have been almost dead. So, oh, 6. I put 6 different batteries in there. Oh, let me get this out of here. All right. and put this back in here. Okay. All right. So the simplest C program is essentially int main return 0. Okay, cool. But a lot is happening here. A function named main is always the entry point to a C program, unlike Python, which enters at the top of the file. Okay, that's a good thing to learn, I guess. Int is the return type of the function here, and is short for integer. Because this is the main function, the return value is the exit code of the program. 0 means success. Anything else means failure. You'll find a lot of abbreviations in C because, number one, programmers are lazy, and two, it used to matter how many bytes your source code was. Okay. The opening bracket is the start of the function body. C ignores white space, so indentation is just for style, not for syntax. Nice. Return 0 returns the 0 value, an integer from the function. Again, this is the exit code because it's the main function. 0 represents nothing bad happened as a return value. The pesky semicolon at the end of return 0 is required in C to terminate statements. Ha! The closing bracket denotes the end of the function's body. It feels insane coming from Python, but printing in C is done with a function called printf from the standard io.h library, standard input output, with a lot of weird formatting rules. To use it, you need you need an include, a hash include at the top of your file. Okay. Then you can use printf from inside a function. Printf. Cool. Notice the new line. It's required to print a new line character. And flush the buffer in the browser, which print in Python does automatically. In case you're wondering, the F in printf stands for print formatted. Okay, so write a small C program that prints program in C. So let's start by including, as they told us to do. Right? Okay. And then let's include the main function, right? Int main. Okay, easy peasy. And then let's run a printf, as they mentioned. And program in C, sure, let's include the new line, as they mentioned as well. And of course, oh, Vim mode not enabled. Let's see, settings. Vim mode, okay. Okay, and then do this. And submit, no, run first, I guess. Oh, shoot. And then we need to return 0. Okay. Okay, did we cover everything here? I guess so, right? So let's submit. And go to the next. Okay, so interpreted quiz. Up until now, you've probably only worked with interpreted languages on boot.dev. Use the following interpreted, in this case Python. Code to answer the question. Print starting. Func that does not exist. Uh-oh. Print finished. Assume that func that doesn't exist is a function that truly does not exist. Okay. What will happen when the code runs? So a stack trace. Okay, so starting prints, then a stack trace, right? Okay, cool. So we won't get to, well, it says ending, but finished. We won't get to finished because we'll see a error, right? Okay, so we'll put that. Okay. C is compiled. This Python code prints starting before it crashes. But in C, it crashes before it can even run. If there's a problem, the compiler tells us before the program even starts. Now, C doesn't tell us about all the possible problems, read skill issues, that might arise in our program, but it does tell us about some of them. Okay, so run the code. Notice that the starting message never prints. Okay, so we had an error at compile time, right? Okay. Fix the bug by removing the non-existent function call. Okay, so now if we run it now, I guess it's fine. Okay. Then let's go to the next. In C, there are two ways to write comments. Ha, nice. So we can do this, /* and */ used to denote the beginning and end of a multi-line comment. Looks like someone on the team doesn't know how to terminate a comment. Fix the bug. Okay. So we missed the slash here, right? Oh, shoot. I forgot that that was set to that key. Okay. I use snakelang btw. Okay. Well, now we know. I use env. No, I don't. Nor arch. Okay. Sorry. All right. Let's go to the next. Oh, a sharpshooter chest. Okay, cool. Let's take a look. Which reminds me. Oh, interesting. I don't know why that didn't appear before. Okay, let's accept the low effort chest. Okay, next. Basic types: int, an integer; float, a floating point number; char, a character; char star, an array of characters. More on this later. If you think about it, it sounds kind of like a string, doesn't it? Oh no. You've already seen int in the example before. It's the return value in the special main function, the entry point for every C program. Someone allowed a Pythonista into our beautiful C codebase. Fix the type bugs on lines 4, 5, and 6. Okay, so let's go to 4. So here in C, what do we generally do? We generally declare what the type is going to be, right? So we put int, we put, char, and we put float, and then we run that. Okay. So that's fine. So far, so good. Strings! Most programming languages these days, even compiled ones, have a built-in string type of some sort. C doesn't. Instead, C strings are just arrays, like lists of characters. We'll talk more about the specifics when we talk about arrays and pointers later, but for now, know that this is how you get a string in C. Okay, so we declare it as char pointer. Okay. You still have 0 users. Darn. Very, I repeat, very. Loosely speaking, char star means string. Also note that it is required to use double quotes. Single quotes make char, not char star. Okay, fix the bug on line 4. All right, line 4. So we'll say it's a char star. Okay. Did I get that right? Oh no, I went forward. Fix the bug on line 4. When is the memory course in C gonna be done? Oh, I guess it is done. Okay, let's go to next. Printing variables. You've already seen me do a printf magic a few times. Unfortunately in C, it isn't as easy to do string interpolation, what f strings do in Python. Instead of print, f string, hello, name, your age, years old. See, that's nice in Python, right? We have to tell C how we want particular values to be printed using format specifiers. Well, this is fine. So common format specifiers are, what do you say, %d, %d digit integer, %c character, %f floating floating point number, %s string char pointer. Okay, printf, hello, string, your digit years old, and then you put the name and age. So it's not the same as Python as they demonstrated, but it's still pretty nice. So new line character. The print function in Python automatically adds a new line character at the end of the string. In C, we have to do this manually. Okay, fair enough. So in the space provided, print default max threads A, custom perms B, constant pi value C, snakelang title D. Use format specifiers to replace A through D with the already provided variables. Okay, so let's just copy this. We'll just paste that here. I think. Whoops. There we go. Okay, so these are going to be strings like this. So we'll go printf. Okay, and so then the max threads we know is an int, so we'll put %d, I guess. We'll include the new line as they emphasized several times. Okay, so then let's put the SnekObjects default. Wait, can we? I thought it was going to have an autocomplete. Okay, so I'll just paste that there. That's fine. Okay, let's not forget this. Okay, cool. All right, next one. We'll go printf, sure. And then here it will be, what? It's a char, right? So we'll put what they said, a C for a char. Okay. Should be good. We'll put this again. And then let's copy this, default perms. Okay. Sorry if I type super slow. Okay, so then a constant pi value. So this one is a float, so we just put f, right? Easy peasy. I mean %f, rather. Maybe it's not so easy peasy. All right, so then we'll put this in here. Okay. Last one. SnekObjects title. So we'll do S for a string. We'll include this, and then let's put this in here. Okay. So we'll hit run. Let's see if we left anything out here. I think we're okay. So default max threads 8 makes sense. Custom perms are sure. Constant pi value 3141590. Sure. And SnekObjects. Okay, so that seems fine. So we'll submit. Okay, let's go to the next. Compilation types. You're probably familiar with the idea of types from Python, but C does them quite a bit differently. In Python, it's okay, but still disgusting, to change the type of a variable. Okay, so we can say x is an int, wow. We can say x is a string, fun. We can say x is a bool, nice. We can say x is a none type. We can say x is, okay, a string again, yay. In C, changing the type of an existing variable is not allowed. Okay, so if I say max threads is 5, but it's a string, and then call bad cop, this is illegal because we tried to put an int in this variable that was already declared as char pointer. Okay, so how do we answer the question? In blank, it's okay to change the type of an existing variable. Python, it is allowed, but still disgusting. Okay, let's go to the next. Variables. As we talked about, variables cannot change types. So we have int main, int x equals 5, float x equals 3.14. Uh-oh, you already declared x. Bad, bad, bad. Okay, so however, a variable's value can change. Okay, so we assigned a 5. We assigned a 10. Oh, this is okay. How come we can assign it again? Because it's still an int. Okay. Run the code, you should get a compilation error. When updating a variable's value, you don't need to redeclare the type. In fact, you can't. Fix the code so that it updates 64 to 32 properly. So it says previous definition, redefinition of SnekObjects int size. I won't allow it. That's probably good. So we'll just get rid of that. And whoops. We'll go ahead and run. Now it says it's okay. Okay, let's go to the next. So a variable's value can change. This is okay. But what if we want to create a variable, create a value that can't change? We can use the const type qualifier. And there is, oh, interesting. There is a link here, but it's to CPP instead of C. Oh, wait. Oh, it is C right here. Oh, okay. All right, cool. Which properly declares a constant in C? So we could say int meaning of life, const equals 42. Oh, we put const in the wrong place. We should put it at the start like they did here. Okay, let's go to the next. Functions. In C, functions specify the types for their arguments and return value. Okay, so the return value should be a float, so that will work. The arguments should both be int. Okay. The first type, float, is the return type. Add is the name of the function. Nice, nice. Int x, int y are the arguments of the function, and their types are specified. Nice, nice. X plus y adds the two arguments together. Float casts the result to a float. Okay, cool. We'll talk more about what cast means later. Type conversion. And the rules for casting to and from certain types. The simple version is that it instructs C to treat the result of x plus y as a float. That's simple, simple. Okay, so here's how you would call this function. So we can say float result equals add 10 to 5. So we just included both the ints, x and y, and some result came out and we printed it, and that's cool. And we got result. Cool. It's nice that C functions enforce returning the same type from all return statements, isn't it? In Python, it can be a pain to realize that a function returns different types depending on the path it took. Yeah, okay. So write a max snakelang memory function in the space provided. It should accept two arguments, int max threads and int memory per thread. It should return an integer representing the total memory available to the snakelang interpreter. Okay, so we'll say it should return an integer. So int, we should say it should be called max snakelang memory. Copy, paste, okay. And then it should take both of these. I'll copy these as well. Okay. Let's go like this. Okay, so then we need a function body, of course. And then return an integer representing the total. Okay, so if we have a certain amount of max threads and memory per threads, then we have to return the product, right? So let's return the product here. Copy again. Because we don't have an autocomplete in this editor, I don't think. Anyway, it's fine. So, let's see what we got here. It says max threads, memory per thread, max memory. Okay, easy peasy. Let's go to the next. Void. In C, there's a special type for function signatures. Void. Void type. Okay. There are two primary ways you'll use void. To explicitly state that a function takes no arguments. Okay, so we could do that. When a function doesn't return anything. So we could do that. Okay, great. So it's important to note that void in C is not like none in Python. It's not a value that can be assigned to a variable. It's just a way to say that a function doesn't return anything or doesn't take any arguments. Okay, so which is not valid? Okay, so this is not valid. We can't use it as a type here, but let's look at the others real quick. Void SSH terminal shop char star address. So this is a function definition or declaration. That's fine. And this is, yeah, these are function declarations, fine. But we can't do this because it's not a variable type. Okay, let's go to the next. Unit tests. Up to this point, we've been checking the standard output of your code against our expected output. Now that you're familiar with functions, most of the lessons will be graded using unit tests. Okay, good idea. In particular, we'll be using the Munit testing framework. Should we say Munit? It's for micro unit, right? Let's see. Unit testing framework for C. A small and portable unit testing framework for C, which includes pretty much everything you might expect from a C testing framework, plus a few pleasant surprises wrapped in a nice API. Okay, cool. All right. Take a look at the main C file. Okay, so this has some things in it. You'll notice it's read-only. You can't change the tests. That would make it too easy to cheat. Ha! It hash includes exercise H at the top. Okay. That's fine. So we can't, is that true? We can't edit this one? Okay, sure. Open exercise H, you'll see the function prototype signature of the function you need to write. In C, the .c files contain the implementation C code, and the .h files are header files that contain the function prototypes. Cool. All right, so here we have it. float, get average, int x, int y, int z. Nice. This allows main C to call the functions implemented in exercise C. Write the get average, mathematical average function in exercise C based on the function prototype expected in exercise H. Okay, so let's just go ahead and copy this and paste. And then let's go ahead and declare like a function body, basically, right? So apparently it's just three things. So we're going to return this float, which is going to be float, or let's see, float x plus y plus z, okay, divide 3.0. Is that what we need to do? Let's take a look. It says test successful, so I think that's good. Before moving on, let's see what was in our tips. The plus operator adds two numbers. Okay, 1 plus 2 is 3. The divide operator divides two numbers. However, if both numbers are integers, integer division is performed. The result will be an integer. If either number is a float, floating point division is performed. The result will be a float. Okay, let's go to the next. Math operators. How much time do we have on the potion? Still 7 minutes? Okay. All the same operators you'd expect exist in C. So we have plus, minus, times, divide, plus equals, minus equals, times equals, divide equals are all the same. We also have increment and decrement. So that's fun. Increment slash decrement operators. The name of C++ is a bit of a joke by the creator. It's meant to be incremented C, or better C. Okay, that's fine. So these increment and decrement operators can be used in two forms, postfix and prefix. Postfix version. The value of x is used in the expression first, and then x is incremented or decremented. For example, so in this case we say int a equals 5, okay. Int b equals a plus plus. So b is assigned 5, then a becomes 6. Okay. Prefix. X is incremented or decremented first, and then the new value of x is used in the expression. So example, a equals 5, b equals plus plus a becomes 6, then b is assigned 6. Okay. Teach says, I generally avoid prefix operators. If I want to increment a variable but keep the original value, I do that in 2 steps. Postfix is more common, especially in loops, which we'll get to. We'll get there. Complete the snake score function in exercise C. Okay, so we've got it already kind of stubbed out for us, but we don't have anything here, so it's not going to work. In fact, if we run, it'll say, oh, you didn't return anything, right? Result must be, oh, never mind. Wait a minute. Did it return something? Maybe I don't understand. So if it's a float but there's no return, so that does compile? Oh shoot. So does it return just 0 then? Kind of like the 0 value in Go. Let's just take a look real quick. C function with no return statement. This is C. If no return statement appears in a function definition, control automatically returns to the calling function after the last statement of the called function is executed. In this case, the return value of the called function is undefined. Oh no. All right, let me close these. All right, so we'll try not to do that. Complete the snake score function in exercise C. Snakeling is unique TM in that its toolchain gives developers a project score that's dependent on how maintainable and high quality their code base is. The larger the score, the harder it is to work in the project. The score is calculated as follows. 1. Multiply the number of files by the number of commits to get the size factor. 2. Add the size factor to the number of contributors to get the complexity factor. 3. Multiply the complexity factor by the average bug criticality, a number between 0 and 1, to get the final score. All right, let's go ahead and do it. So I'll just get rid of that. So first we want a size factor. So the size factor is the product of num files and num commits. So we'll say int size factor, and we'll assign to num files multiply num commits. Okay, so that's fine. Then it says step 2, we should add the size factor to the number of contributors. So those are both ints. And we'll get the complexity factor. Okay, so let's say that's a size factor. Okay, added to number of commits. Sure. Okay, and then multiply the complexity factor by the average bug criticality. So we'll get float, and then we'll say final score, and we'll say that is complexity factor multiply average bug criticality, and return final score. Okay, let's see what we get here. Whoops. Okay. Uh-oh. Result must be 1.9. Okay. Oh, I got 2. Let's see. Float final score. Okay, I think we're gonna do float complexity factor. Just gonna do it like that. Is that what we needed? No. Okay, messed it up. Okay, average bug criticality, complexity factor. Oh. Okay, let's see. Result equals 1.9. 2 equals, result must be, so I got 2. Darn. Darn, okay. What did I do wrong? Return, okay, so float final score, complexity factor times average bug. Oh no. Let's see the tip. You can convert an integer to a float by casting it. Okay. Messed it up. I don't know. I don't know. Okay. Complexity factor multiplied by average bug criticality and no luck. Float. Okay, so num commits. Okay, let's see. Should we just show the complexity factor here? Let's put this. And here show the final score. And here show the average bug criticality. Okay, let's look. Oh, of course. Let's see here. So it says we have 20. Okay, we have 0.1. All right, and then it says 2, but result must be 1.9. Okay, so I guess I must have screwed this up. So it was probably supposed to be 19 and not 20. Okay, so num files. All right. Okay, so num files here, and num commits, Let's see what we got. Okay, so 3 and 5. So we multiplied those and got 15. Oh, wait a minute. There's my mistake. I think it was num contributors and I didn't realize that until just now. Well, that's careless. Okay. All right. Okay, then let's get rid of these prints. Okay, so that says okay. Man, talk about messed up. How much is on here? Oh, my potion ran out. Okay. I have to go take a quick break and come back in probably 5 minutes. Probably 5 minutes. All right, back at it. Right back at it, baby. If statements. Here we go. Let's take a real quick look here. Okay. Okay, let's take a look. If statements are the most basic form of control flow in C. Very similar to other languages. Cool. Basic syntax. So in this example, we say if x is greater than 3, printf x is greater than 3. Nice, nice. If, else, and else if are also available. So we can say if, we can say else if x is 3, x is less than 3. Okay. Janky syntax. You can write an if statement without braces if you only have one statement in the body. Cool. But this shorthand is easy to mess it up and in my opinion isn't worth saving a couple lines. There are enough ways to shoot yourself in the foot in C already. Fair enough. Take a look at exercise H. Write the implementation for the function prototype found there back in exercise C. It should calculate whether the temperature is too cold or too hot. In Fahrenheit, of course, the most reasonable scale for regular living. Less than 70 returns too cold. More than 90 returns too hot. Otherwise, return just right. Hey, do not add the /n to the end of the string, to the \n, the new line. That's done at print time. Okay, so we'll take this. See if we don't mess it up like before this time. So we'll paste here, and then let's take a look. So we'll go ahead and do one of these, and then it's get temperature status. So we want to do one of these strings depending on which it is, right? So we'll say if temp is less than 70, so that's an int, then we'll return too cold. Okay. So then here we'll say else if temp is greater than 90. Oops. Okay, so here we'll say too hot, and then here we'll say else, and here we will say, oops, just right. So it says 2 of 2, 100% test successful. Did we do a potion again? Let's activate XP potion, baby. Oh yeah. Okay, that seems fine. Let's go to the next. Ternary. Man, we've been in C basics for a while. This is gonna take me forever. I've already been here for like more than 30 minutes. All right, it's fine. Like JavaScript, C has a ternary operator. So let's break down the syntax. So we said int max equals A is greater than B. Well, if so, A. If not, B. All right. The entire line is a single expression that evaluates to one value. Here's how it works. A greater than B is the condition. A is the final value if the condition is true. B is the final value if the condition is false. The entire expression, A greater than B, if so, A, if not B, evaluates to either A or B, which is then assigned to max in our example. Ternaries are a way to write a simple if/else statement in one line. My recommendation, don't use... What the... Okay. Okay, just kidding, they're fine. Just don't use them like a JS Andy on every single line to just save 3 keystrokes. Now, I think that's a little unfair. People use these a lot in JSX, because in JSX you have to use expressions, not statements. I find them most useful when you are trying to set a single value to the result of some Boolean expression, like max in the example above. Generally speaking, I think you're better served with if statements in C. That seems perfectly reasonable. All right, so let's answer the question. What's the result of 1 equals 0? Oh, wait, this is false, so now we have to put F. Okay, that's fine. Let's go to the next. Type sizes. In C, the size in memory of a type is not guaranteed to be the same on all systems. That's because the size of a type is dependent on the system's architecture. For example, on a 32-bit system, the size of an int is usually 4 bytes, while on a 64-bit system, the size of an int is usually 8 bytes. Of course, you never know until you run Sizeof with the compiler you plan on using. However, some types are always guaranteed to be the same. Here's a list of the basic C data types along with their typical sizes in bytes. Note that sizes can vary based on the platform. For example, 32-bit versus 64-bit systems. So, char, size 1 byte, represents a single character. Note, always 1 byte, but can be signed or unsigned. Wow, really? Okay. Float, size 4 bytes, represents single precision floating point number. Double, size 8 bytes, represents double precision floating point number. Nice. The actual sizes of these types can be determined using the Sizeof operator in C for a specific platform, which we'll learn about next. So the size of a data type is the same on every computer in C? False. Let's not make that assumption. Sizeof. C gives us a way to check the size of a type or variable. Sizeof. Sizeof operator. Cool. You can use sizeof like a function, although technically it's a unary operator. Unary operation. But that distinction is generally only useful for winning super important internet arguments. Okay, well, if we learn nothing else, let's keep this one in mind. Sizeof is a unary operator. Okay, so we'll use the sizeof operator in the next few lessons to give us insight into the memory layout of different types in C. This will be particularly useful as we move deeper into C, and essential for understanding pointers. Pointers are not too bad once you understand the basics. I promise. Well, we'll see how this goes. All right, size t. The size t type is a special type that is guaranteed to be able to represent the size of the largest possible object in the target platform's address space, i.e., can fit any single non-struct value inside of it. Okay. That's cool. That's cool. So it's also the type that sizeof returns. Okay. So run the function to see the size of a char. No. Okay, so size of char equals 1. Okay, fair enough. Update the main to also print the size of each of the following types in order. Okay, so let's go ahead then and we'll just copy this, I guess. Probably, and then let's put this in here. So we need the bool, the int, the float, the double, and the size t. Okay, let's take a look. Okay, so we got the char, sure. Okay, so this next one is going to be the bool. Okay. This next one will be the int, sure. Oh wait, I've got extra double quotes in here all over the place. I didn't mean to copy those. That's a skill issue for sure. Okay. Okay, so we'll do size of char there. Okay, so we have int. This one should be float. This one should be double. And this one should be size t. Okay, cool. And then let's copy these. Right, so copy that. Paste, so we'll get the bool, the int, the float, the double, and the size t. Okay, so this one will be the bool. This one will be the int. This one will be the float. This one will be the double. And this one will be the size t. Yeah? Size of char. Uh-oh. Well, it didn't effing work. Let's see here. Oh. Okay, size of char 1, size of bool 1, okay. Size of int 4, size of float 4, size of double 8, size of size t 4. Okay. Is that all we needed? Take a look at the results before moving on. Notice that a char only takes up 1 byte, which is 8 bits, while the other types take up more space. Well, except for the bool, I guess. All right, so let's submit that. Okay. For loop. Cool, let's do it. So, a for loop in C is a control flow statement for repeated execution of a block of code. Very similar to Python, but with a different syntax. The syntax of a for loop in C consists of three main parts. 1. Initialization. 2. Condition. 3. Final expression. There is no for each iterables in C. For example, there's no way to do for car in cars print car. Instead, we have to iterate over the numbers of indices in a list, and then we can access the item using the index. Okay. Okay, so it's a 3-clause for loop with initialization, condition, and final expression. Sure. Initialization, executed only once at the beginning of the loop, is typically used to initialize the loop counter, int I equals 0, for example. Condition, checked before each iteration. If true, execute the body. If false, terminate the loop. Often checks to ensure I is less than some value, I less than 5, for example. And then final expression, executed after each iteration of the loop body, can be used to update the loop counter or run any other code, I++, for example. And then the loop body, the block of code that is executed while the condition is true. So, example of a basic loop, we said for int I equals 0, I less than 5, I++, we printf the I, and then we should get them printed here. So that's fine. Implement the print numbers prototyped in exercise H. Okay. And that takes a starting number and an ending number and prints all the numbers in that range inclusive using a for loop. Okay, so let's say, do we need to check whether start is less than end? You know what, let's just take a look. It's only going to test it with 42 and 69, so let's not worry about whether start might be less than, or whether start might be greater than end, excuse me. We're only testing it with these, so we'll just do this with the assumption that start is less than end to start with. So we'll say for. So then I guess we don't really need to initialize anything, right? Because we already have start. But let's just do it like this. We'll say I equals start. So we'll just use a separate int. That's fine. And then we'll say I less than end. Cool, that's fine by me. And then we'll say I++, sure, easy peasy. And then we will printf. And then we'll just put the number the way they did there. And that is fine. And then it's void, so I guess we don't need to return. And let's see what we got. So we got the numbers shown. Whoops. What the heck? Oh, I have my hand on the wrong key. Only a few characters off. Okay, so it was supposed to include the last number, and it was even bolded, and I just didn't pay attention. Okay. All right, so that's ironic. Okay, let's go to the next. While loop. A while loop in C is a control flow statement that allows code to be executed repeatedly based on a given Boolean true/false condition. The loop continues to execute as long as the condition remains true. Okay, so while. So parts of a while loop. Condition checked before each iteration. If true, execute the body. If false, terminate the loop. Loop body. The block of code that is executed while condition is true. Okay, so here's an example. So here, we ended up doing the same thing as in the other one, right? Except now we just declare the I before, and then we do the ++ inside the body. Easy peasy. The condition is evaluated before the execution of the loop body. If the condition is false initially, the loop body will never even start. If the condition never becomes false, you will get an infinite loop. All right, cool. So we'll implement the print numbers reverse. Whoops, I don't know what I pressed there. Okay, print numbers reverse. And it takes a starting number higher and an ending number lower and prints all the numbers in that range from highest to lowest inclusive, this time using a while loop. Okay, so we'll just do it like last time, except we know this time they're counting down. And we're just going to go 20 to 4. So we'll say, we'll just do it like they did. So int I equals start while I is greater than or equal to, it's still inclusive, greater than or equal to end. And then we'll print f, and that will just be like this. Then we will I minus minus. Okay. And you know, since they spent the time to teach us about how this works, let's just put it there. Sure, okay. So we got down to 4. Okay. This is crazy because my potion is still running, but I gotta step away for a second again. I'll be right back. Okay. All right. Let's hop back on here. Okay, so we just run that. Okay, let's take a look. Okay, fine by me. Let's go to the next. Do while loop. A do while loop in C is a control flow statement that allows code to be executed repeatedly based on a given Boolean condition. Unlike the while loop, the do while loop checks the condition after executing the loop body, so the loop body is always executed at least once. Okay, so parts of a do while loop. So the loop body is the block of code that is executed before checking the condition and then repeatedly as long as the condition is true. Condition is checked after each iteration. If true, execute the body again. If false, terminate the loop. Okay. So, yep, this seems fine. Oh, this time we showed two examples. So in this case, we do the same thing as before. Okay. Don't know what to say about that necessarily, but in this case, we start at 100. Okay. And then we do this while I is less than 5. Okay. So it'll only happen once because this will be false. So it just says 100. So key points. The do while loop guarantees that the loop body is executed at least once, even if the condition is false initially. The most common scenario you will see a do while loop used in is, you will see a do while, the most common scenario you will see a do while loop used is in C macros. They let you define a block of code and execute it exactly once in a way that is safe across different compilers and ensures that the variables created/referenced within the macro do not leak to the surrounding environment. If you end up looking at any source code for macros, you will probably see a few do while loops. For example, here's a simplified version from our Munit testing library we're using. Okay, so a simplified version. So in this case, we have a do while, and we put a 0 here. Oh, interesting. So it will only happen once. It creates a do while. Wait. Execute it exactly once in a way that is safe across different compilers and ensures that the variables created/referenced within the macro do not leak to the surrounding environment. Okay. So these are all inside the loop block only. Checks that the assertion is valid. If it is not, then it errors and formats a complicated error message. If this code doesn't make any sense, that's fine too. I think it probably makes enough sense. So, I mean, if we start with the error message, assertion failed, it has 3 strings, and then, oh, wait a minute. Oh, Munit error F. Oh, actually, okay. Nope, I'm not too sure. Not too sure how it works. And then these are with hashes. Okay. Yep, I think it doesn't make any sense to me, sorry. I just wanted to show you where they most often occur. Note there is no semicolon after the while 0. This lets the macro be used in a block of code without causing syntax errors. Okay. Interesting. Okay. All right, so let's run this code. Prints 5 through 1. Okay, 5, 4, 3, 2, 1. Sure. It doesn't print anything from 1 through 5 because the condition of the while loop is never true. Okay. So we did 5 through 1, and then we did 1 through 5. Okay. Change print numbers reverse to use a do while loop so that it always at least prints the starting number. All right. So we'll get rid of this, I guess, and put it here. And then here we'll put do. I left out the semicolon. And is that it? So printing from 1 to 5. So it says change print numbers reverse to use a do while loop so that it always at least prints the starting number. Okay, if that's what we want. Let's go to the next. Oh, that's our low effort chest. Interesting. This one's paying out pretty generously, I guess. Even this one is okay. A difficulty 5 is not that high. It does seem like it's paying out pretty generously though. Okay, so Pragma wants and header guards. We saw how H header files are used in a previous lesson, but before we go further, let's talk about a potential issue you might run into. Multiple inclusions. If the same header file gets included more than once, you can end up with some nasty errors caused by redefining things like functions or structs. Pragma wants one simple solution, and the one we'll use for the rest of this course, is Pragma once. Adding this line right here to the top of a header file tells the compiler to include the file only once, even if it's referenced multiple times across your program. All right, header guards. Another common way to avoid multiple inclusions is with include guards, which use preprocessor directives like this. So, if not defined, my header h define my header h. Some cool code, and if. All right. This method works by defining a unique macro for the header file. If it's already been included, the guard prevents it from being processed again. Throughout this course, you'll see Pragma once in our header files. It's quicker and less error-prone than traditional include guards, and it works well with most modern compilers. So what is the purpose of the Pragma once in a header file? Prevents the header file from being included more than once, avoiding redefinition errors. Right? So does it improve the performance? No. Does it automatically generate function prototypes? No. Does it allow a header file to be included multiple times in the same program? No, it prevents it. Okay, let's go to the next. Still got 4 minutes. Okay, so what are structs? So far, all we've seen are the simple non-collection types in C. However, stuff like this can get really annoying. So let's look at this example. So x1, y1, z1 is x2, y2, z2. Interesting. x1, y1, z1, x2, y2, z2. So the distance equals the distance of x1, y1, z1 to x2, y2, z2. Okay, so instead, we could have used a struct, right? So our distance function starts to look ridiculous. It's int distance, which takes these 6 ints, x1, y1, z1, x2, y2, z2. Okay. We also run into a new problem. In C, we're only allowed to return a single value from a function. This doesn't work, so scale coordinate. X times scale, y times scale, z times scale, too many values to return. Messed up. So we can solve this using a struct. Here's an example of the syntax. Struct human, int age, char, star name, int is alive. Okay, cool. So, Snakelang has built-in support for graphics programming and vows to never gouge game devs. Wow. Define a new struct called coordinate in coord h. Alright. Remember, h files are for declarations of types and function prototypes. The coordinate struct should have 3 fields. Okay. So we'll put x, so int x, cool. Int y, sure, and int z. All right, I guess that's all we want. Okay, so we can submit that one and go to the next. Okay, initializers. So now you're probably wondering, hey TJ, so how do we actually make an instance of a struct? You may have noticed in the previous lesson, all we did was define the struct type. Unfortunately, there are a few different ways to initialize a struct. Interesting, interesting. I'll give you an example of each using this struct. So it's called a city. It has the char star name, the int lat, and the int long. All right. So we have the 0 initializer. So we say struct city c equals 0 in curly brackets. Interesting. So this sets all the fields to 0 values. positional initializer. So in this case, we said San Francisco 37 minus 122. Okay, cool. Designated initializer. This is my generally preferred way to initialize a struct. Why? It's easier to read, has field names. If the fields change, you don't have to worry about breaking the ordering. Remember, it's dot name, not name. If this trips you up, just remember it's dot name and not name, because that's how you access the field, e.g. c.name. Okay, cool. So accessing the field in a struct is done using the dot operator. For example, if we have the struct city C, then we can set the latitude by saying c.lat equals 41. And then we can print the latitude, printf latitude, and put c.lat here. Okay, cool. Note there's another way to do this for pointers that we'll get to later. Okay, it's going to be important. So let's complete the new coord function. It accepts 3 integers and returns a coordinate. Use the designated initializer syntax because I said so. Okay, cool. So let's just do this. So we'll say that the struct. Oh, I'm gonna fix my posture a little bit. Okay, struct coordinate, and we'll say, well, let's see. Should we just return? Let's try this first. I'm not sure if this is technically allowed, but let's just try. So dot x equals x, dot y equals y, dot z equals z. Nope. Okay, so it says expected expression. So we won't do that. We'll say struct coordinate, and I'll just say c equals, and we'll say return c. Wait a minute. Okay, so it looks like that's successful. I think I left out the actual semicolon before, right? So let's just try this again. Whoops. Okay, no. So we couldn't do that. We could not do that, but this is okay. All right, let me try one more thing. So, I might try a couple more things. We'll see here. So what if we were to go return, and then what if we were to try to use this positional? I don't think that's going to work, but let me just try. I don't know. So just say x, y, z. I don't know. Try it. Nope. All right. Okay. So this way is fine, I think. Okay, let's go to the next. Scaling coordinate. Okay, so remember how we can not return multiple values from a function in C? So we can't do this. So in this example, we try to define a function that returns 2 different types, but the compiler won't allow it. Let's just try putting it in here real quick. Yeah, it says expected identifier or parenthesis. Anyway, so we can't do that. Whoops. We can accomplish effectively the same thing by returning a struct. So instead of trying to say int and char, we do a struct that has the age and name. Okay, cool. So open chord H and add a declaration for the scale coordinate function as defined in the chord C file. Okay, so let's copy this. Okay. And then complete the scale coordinate function in chord.c. It should return a new coordinate where each field is scaled up multiplied by the factor parameter. All right, cool. So let's just say struct coordinate chord equals, right, similar to up above. And then we'll say, oh wait, this one's already called chord. I'll just call mine, C. Yeah, sure. Chord.x times factor. Is that okay? They're all int, so I guess so. Dot y equals chord y times factor. Sure. And z equals chord z times factor. All right, by me, so we'll return C. Okay, something like that. Okay, let's, oh, we need another potion, baby. Okay, I'll do it before I submit the next one. Typedef. So by now you're probably tired of typing struct coordinate over and over again, and you're wondering, how can I make my struct types easier to write, like int? Okay, so good news, C can do this with the typedef keyword. Cool. So we defined something here, struct pastry, or like struct coordinate, but we can also write this as typedef. Okay, so we added typedef to the start, okay, and then it's the same here, but then we added pastry underscore t. So now you can use pastry t wherever before you would have used struct pastry. Note, the t at the end is a common convention to indicate a type. All right, fair enough, fair enough. So in fact, you can optionally skip giving the struct a name. Okay, so that's cool. So we can typedef like this. So in this case, you'd only be able to refer to the type as pastry t. In general, I do give the struct an actual name, e.g. pastry, but I only use the typedef type. We'll be using this convention in this course. Okay, cool. So update the new chord and scale coordinate functions to use the coordinate t type instead of struct coordinate, and then update the coordinate declaration in chord h to use typedef to create a new type called coordinate t. Okay, so we'll go here and we'll put typedef, and here we will put coordinate t. Sure. I'll leave these ones alone. It didn't say to change them, and I guess they're probably still fine as they are. But when we go into here, we'll do what this said. New chord function, use the coordinate t type instead of struct coordinate. Okay, so let's see. We'll say coordinate t, right? And then here as well. And here, I should be doing find and replace, right? It says JavaScript regex. I don't know. Okay, so let's run. Okay. Okay, we included chord H, typedef struct coordinate, like this. Oh, I have a coordinate too? Okay. That's a brain fart. Okay, let's go to the next. Oh, I didn't hit the potion like I said I was going to. That's a double brain fart. All right. As we saw earlier, sizeof can be used to view the size of a type. For once, programmers thought of a name that was actually helpful. But this isn't just true of built-in types like int or float. You can also use it to find out the size of structs. Okay, cool, cool. So structs are stored contiguously in memory, one field after another. So take this struct. So it has 3 ints inside. Assuming int is 4 bytes, the memory layout for coordinate t would look like x, y, and z, and each is 4 bytes. Okay, easy peasy. We can also have mixed type structs, right? So we have a char, an int, and a double here. So if the char is 1, the int is 4, and the double is 8, then we put 1 here for the char, okay. Then apparently we have padding, I guess, all right. Then we have 4 bytes, and then we have 8 bytes. Okay, so tell us about the padding, baby. So what is the padding doing here? Turns out that CPUs don't like accessing data that's not aligned. Data structure alignment, all right. Incredible oversimplification alert, since obviously CPUs don't have feelings yet. So C inserts padding to maintain alignment. For example, every 4 bytes in this example. Okay, so huge caveat. These layouts can vary depending on the compiler and system architecture. Okay, good to know. All right, so it's just a quiz question here this time. Let's hit the potion. Cool. Size of struct will always return in the same value as the sum of size of field for each field in the struct. So we saw that that is false, right? Because this one, if we added 1, 4, and 8, we would miss the 3 bytes of padding, so false. Struct padding. So there are a bunch of complicated rules and heuristics that different compilers use to determine how to lay out your structs. But to oversimplify, 1. The fields of a struct are laid out in memory contiguously, next to each other. Structs can vary in size depending on how they are laid out. So C is a language that aims to give tight control over memory. So the fact that you can control the layout of your structs is a feature, not a bug. Compilers plus modern hardware plus optimizations plus skill issues means that sometimes what you think the computer is going to do isn't exactly what it actually does. That said, C is designed to get you close to the machine and allows you to dig in and figure out what's going on if you want to go for a specific compiler or architecture. As a rule of thumb, ordering your fields from largest to smallest will help the compiler minimize padding. Okay, cool. So in here, we put a char, and then we put a double, and then a char, and then a char, and then a long, and then a char, and we said it was poorly aligned. Darn. But in this case, we went largest to smallest. So we started with the double, then the long, and then all the chars last. Okay, so better. Okay, so the assignment is rearrange the fields in SnekObjects var t so that the padding is optimal and the tests in main C pass. Okay, let's see what the tests say to begin with. The tests say... Assertion failed. Size of SnekObjects var t equals 16. Oh no, we got 20? Tisk messed up, baby. Alright, so we're supposed to put the chars at the bottom. So let's get rid of these and put them here. And this one here. And I guess that's it, right? Okay, let's go to the next. Memory. Before we talk about pointers, we should talk about variables and memory in general. Here are some useful, albeit hand-wavy, mental models. Okay, so variables are human-readable names that refer to some data in memory. Memory is a big array of bytes, and data is stored in the array. A variable is a human-readable name that refers to an address in memory, which is an index into the big array of bytes. Here's a diagram. Okay, so we have a variable name, value tej, address 0, size 4 bytes, okay. And then a handle, Typedef, address 4, size 8 bytes. Okay, so what we're looking at here is chars in each spot, right? So tej, T-E-E-J, and then Typedef, T-E-E-J, underscore D-E-V. That's what we're looking at, right? So getting a variable's address. In C, you can print the address of a variable by using the address of operator. Here's an example. So it's the and. So in this case, we put the age is 37, but then we put the address of age is, and then we put P for pointer, right? The P format specifier will format a pointer to be printed. Nice. So that's a memory address. So we got the address of age here. Okay, cool. And then it shows the address of age is 0xFFF8. Amazing. Okay, so assignment. The size of address function accepts a long, a potentially very large integer, as input and returns the size of its address. There's a bug! Memory addresses in Snakelang should always be 4 bytes long. Fix the function so that it prints the size of i's address, not value. Okay, so let's see what it says now. So it says 8, because the long size is 8. Okay, so we'll just keep in mind that we can get the pointer by using this address of operator. And did they have a link for us on this one? Looks like we had no link on this one, but let's take a quick look. Address of operator. You think that's how it is? So it's the operator and. So obtain the actual address of the object or function arg even in the presence of overloaded operator and. Okay. Would you overload that operator and? I guess you can. All right. Okay, so did it work if we do this? Yeah, test successful. Sure. Let's go on to the next. Okay, so we have plenty of time left on the potion. So what is an address? What is an address? So I mentioned in the last lesson that memory can be thought of as a big array of bytes, and each byte has an address. That's true, and the beauty is that each address is literally just a number. It's not some immortal address like 1234 Elm Street or 1600 Pennsylvania Avenue. It's just a number. You might be thinking, hey, if it's just a number, why does it look all disgusting? Is that what we're thinking? Yeah, why does it look all disgusting? Like 0xFFF8. Okay, so it's just a number in hexadecimal. All right, pretty big number, so not very human readable. It's the same as 65,528. All right, whatever. So this is fine. So we have green hexadecimal and blue decimal. Easy peasy. So which looks most like a memory address? 11Z's. Take the second circuit past the transistor, then a hard left. 221B Baker Street, London. Or a long hex code. Let's choose the hex code. Okay, virtual memory. As it turns out, your code probably doesn't have direct access to the physical RAM in your computer. Instead, your operating system provides a layer of abstraction called virtual memory. Virtual memory makes it seem like your program has direct access to all the memory on the machine, even if it doesn't. So the physical memory is the actual RAM stick in your computer. The operating system is the software that manages access to the physical memory. Your program, when it runs, it becomes a process and is given access to a chunk of virtual memory by the operating system. And this virtual memory, this abstracted chunk of memory that your program can use. Okay. So there are exceptions to this. For example, if you're using C to build embedded firmware that runs without an operating system, your code might interact directly with physical memory. Good to know, baby. And look, isn't this a nice diagram? So we have a program in kind of an oval thing, kind of an ellipse here. It says I can has memory to the operating system. And the operating system has some access to physical memory here. It says knock yourself out, and says here, take, enjoy, virtual memory. By only giving processes access to a chunk of virtual memory, the operating system can do some cool things. 1. Isolation. One process can't access the memory of another process. That's good. That's good. We don't want to allow them to do that. Security. The operating system can prevent processes from accessing certain parts of memory. Simplicity. Developers don't have to worry about managing physical memory and the memory of other processes. Performance. The operating system can optimize memory access depending on the hardware and needs of the program. For example, by moving data between physical memory and the hard drive. Very nice, very nice. So at the end of the day, your program has direct access to a virtual chunk of memory. Just like physical memory, it can be thought of as a big array of bytes where each byte has an address. Okay, so are the memory addresses that your code sees the same as the physical addresses in RAM? It's not always, it's not never, but it's if we're using the operating system, then we're going to say most likely not, because the operating system provides a virtual address space. Okay, let's go to the next. Pointers. You've probably heard of pointers. You may have also seen jokes about how they are impossible to learn. Well, that's wrong. In fact, now that you understand how memory is laid out in an array, a lot of the mystery behind pointers should be gone. You know, I don't think that what people complain about with pointers is that they are a mystery, but it's cool. It's cool. Let's go. Let the man cook. So, put simply, a pointer is just a variable that stores a memory address. It's called a pointer because it points to the address of a variable which stores the actual data held in that variable. A pointer is declared with an asterisk after the type. For example, int star. Okay, so int age equals 37, and the int star pointer to age is set to the address of age. Amazing. So remember, to get the address of a variable so that we can store it in a pointer variable, we can use the address of operator, and. Amazing. So learning about pointers is easy. Sure, let's go. Why pointers? So to illustrate the usefulness of pointers, let's pretend we want to pass a collection of data into a function. Within that function, we want to modify the data. In Python, we could use a class to store the data and pass an instance of that class into the function. Okay, so here's a Python OOP code with a class. So it has an init, that's fine, and then it has an update, and so if you pass this guy in there, then it will say the coordinate x is the new x, sure, and then we say c equals coordinate 1, 2, 3, print c.x, we get a 1, and then we do update coordinate x, and we do c4, and print c.x, it's now 4. I mean, okay, easy. Now let's do the same thing, but using a struct in the C. So complete the coordinate update x function, and the coordinate update and return x functions. Okay, so we can update returning void, or we can update and return x, but it returns coordinate t. Okay, and so here we have these here. All right, so I mean, I'm just gonna say, wait a minute. So, oh, okay. So let's go ahead and fill these both in, but we're just gonna do it just like this, but that's not right? We're gonna do it the wrong way first, it looks like. Let's see what happens. So we'll just put core.x equals new x. Okay, and in this one, we'll just do let's just copy this. And we'll put in the core and the new x, and then we'll return core. Yeah? Okay, so now what happens? Uh-oh. Okay. It says successful. Okay, so let's look at the test cases. After passing the assignment, open up main C. Wait a minute. Okay, so I guess we are fine here. I guess I misunderstood what the point of this was about to be. Oh, no, it says wrong. It says after passing the assignment. Oh, interesting. So I got a 1. New.x must be 4. Okay. So here, so the point here was that we want to say, so coordinate update x doesn't update anything, but coordinate update and return x does, because it returns a new copy of the struct. Okay, let's see. So we'll say okay, so we did do it wrong at first, right? Interesting. So notice that coordinate update x doesn't update anything, but coordinate update and return x does because it returns a new copy of the struct. Okay, so let's find it. So we did one where we did coordinate update x, and then old x must still be 1 here. Okay, that's fine. And then in this one, we used update and return, so old x must still be 1. But the new x is 4. Okay. And then they have different addresses. Assert pointer not equal must be different addresses. All right, so in C, structs are passed by value. That's why updating a field in the struct does not change the original struct from the main function, okay? To get the change to persist, we needed to return the updated struct from the function, a new copy. The memory address of the struct that went in to coordinate update and return x was not the same as the address of the struct that was returned, again, because we created a copy. Okay. Cool, interesting. So that's neat. And of course that's different from Python because in Python, this object is passed by reference, right? Okay, cool. So that's good to know. So let's go on to the next, I guess. How much time do we have on the potion? 14 more minutes? Okay. Pointer basics. Oh man, there is so much here. I'm going to be here all day, and that's fine. All right, so pointer basics. Remember, pointers are just an address, read a value, that tells the computer where to look for other values. Okay, so just like how the address to your house is not actually your house, but points you to where your house is. Okay. So we can declare a pointer to an integer, int star pointer to something. Okay. Get the address of a variable, the meaning of life. Pointer to meaning of life is the address of meaning of life. Okay. So dereferencing pointers. So this is new. So oftentimes we have a pointer, but we want to get access to the data that it points to. Not the address itself, but the value stored at that address. We can use an asterisk to do it. The asterisk operator dereferences a pointer. So the meaning of life is 42. Okay, we did this already. And now the pointer to the meaning of life is the address. All right, so what's the value? So now we dereference. So we go star pointer to meaning of life. That dereferences. Okay. So it can be a touch confusing, but remember that the asterisk symbol is used for two different things: declaring a pointer type and dereferencing a pointer value. So that's what we've got. Int star pointer to thing, that's declaring a pointer type. And dereferencing is we say star pointer to thing equals 20. Okay. So we can fix the change file type function both in the C and H files. Okay, so let's take a look here first. It should accept a pointer to a code file. Okay, so here, let's say that this is going to be star so that it's a pointer. Dereference the pointer into a code file t struct. Change the file type field to the provided new file type value. Return the updated code file t struct. Okay, so this has lines and file type. Okay, so again here we'll put the star. All right, so code file t new f equals address of f. Okay, well it shouldn't be address of f, it should just be f dereferenced, right? Whoops. So we should dereference, I think. New f dot file type equals new file type. Okay, sure. Return new f. Okay, so we dereferenced the pointer into a code file t struct. Okay, cool. Change the file type field to the provided new file type. Return the updated code file t struct. Okay, let's see what we get. Another sharpshooter chest. Man, they're generous with these. Okay, got a new potion. Cool. All right, so we'll go to the next. Okay, pointers to structs. As you know, when you have a struct, you can access the fields with the dot operator. All right, so in this example, we have a coordinate t point, and it's 10, 20, 30. And then we can print the digit here by going point.x. Okay, so however, when you're working with a pointer to a struct, you need to use the arrow operator. Okay, cool. So this time we use the pointer and then we arrow to the x. So it effectively dereferences the pointer and accesses the field in one step. To be fair, you can also use the dereference and dot operator to achieve the same result. It's just more verbose and less common. So they put star pointer to point, they put it all in parentheses and put dot x. Okay, easy peasy. All right, so order of operations. The dot operator has a higher precedence than the star operator. So parentheses are necessary, right? Parentheses are necessary when using star to dereference a pointer before accessing a member, which is another reason why the arrow operator is so much more common. Okay, so which is the odd one out? Which of these options is not equivalent? So the odd one out is this one, because this is dereferencing the field, which isn't going to work because this is a pointer, so it's not a struct, so we can't even do it. But these and these are both fine. Okay, so let's go to the next. So C arrays. So if you're used to lists in Python, arrays in C are similar, but a bit lower level. So an array is a fixed size ordered collection of elements. Like Python lists, they are indexed by integers starting at 0. Unlike Python lists, they can only hold elements of the same type. They are stored in contiguous memory just like structs. Cool. So an integer array example, we could say int numbers, and there's 5 of them, and we put 5 in here, 1, 2, 3, 4, 5, okay. Iterating over an array. So in C, there's not a for x in list syntax. Instead, you must iterate over them using a for loop with an index or some other conditional loop. Okay, so we said int numbers 5, 1, 2, 3, 4, 5. Then we said for int I equals 0, I less than 5, I plus plus. So notice we put 5 here both places. So we're probably going to want to store that array length separately, but we'll come back to that, I think. So updating values in an array. So the syntax for updating values in an array is the same as how you access them. So we put r sub index equals value. So using our numbers example, so we declare the numbers here again. We changed the 1, so we changed the 2 here at index 1 to a 20. Then we go here, index 3, change it to 40. Okay. So we print each one in turn, so we should get our 1, 20, 3, 45. Okay, fine. Okay, so complete the update file function. The file data array is a large 200 integer array representing a snake-laying source file. Each integer in the array represents a special piece of data. So at index 1, we have the number of lines. Index 2 is the file type. Index 199 is always 0. Okay. So here we go. So we're ready to go here, right? So we're going to say file data sub1 equals new num lines. Oh gosh. Okay, so this one is 2, and that's going to be file type. And then we are going to say 199 is going to be 0. Right? It says test successful, so I guess that's what we want. Let's see. Okay, let's go to the next. How much time on the potion? 6 minutes. Okay, so arrays as pointers in C. In C, arrays and pointers are closely related. An array name acts as a pointer to the first element of the array. That means array indexing and pointer arithmetic can be used interchangeably to access array elements. Let's go through this step by step to understand how this works. All right, step by step. Array declaration. Int numbers sub 5 equals 1, 2, 3, 4, 5. Okay. So here, numbers is an array of 5 integers. Array is pointer. The name numbers acts as a pointer to the first element of the array. Okay. So we can say the int star numbers pointer equals numbers. Okay, so that works just fine. Numbers pointer is a pointer to the same place as numbers. Okay, so that works. Accessing elements via indexing. So access the third element, which is at index 2, sure. It's the same as int value equals, so we take the numbers pointer, add 2, and then dereference, right? Numbers plus 2 computes the address of the third element, and star dereferences it to get the value. Okay, cool. Pointer arithmetic. When you add an integer to a pointer, the resulting pointer is offset by that integer times the size of the data type. All right. So if we put int star p equals numbers plus 2, now p points to the third element. And the value is 3. Okay, cool. What else? Diagram explanation. Okay, so let's assume numbers is stored starting at memory address 0x1000. I shouldn't say 1000, it's a hex code. So an integer is typically 4 bytes in C. Here's how the array elements are laid out in memory. All right, so at this address we have this value, then we offset by 4 for the next, because this was the size, right? 4 bytes. So we offset by 4 each time. So we end up at 8, we end up at C, and then we end up at 10. Because, of course, the C represents 12 and the 10 represents 16. All right, what else should we say? So accessing elements using pointers. So numbers plus 0, or the address of numbers sub 0, points to the 1000. What is 1000? It should be, let's see, 10 is 2, no, they're in hex, so I don't remember what they are. So 10 is 16, 100 is 256? No. Is it? I don't remember what they are. And I don't know what 1000 is. 16, it's yeah, 16 to the third. Okay, so in the example code, we do this. We declare our array of numbers. Then we print whatever is at this index number 2. So we get the 3, which we had here. Cool. We can access using pointers. So we do the same thing. We get the 3 again. All right. Pointer arithmetic. So we can do pointers. All right. So it starts at the beginning. That's fine. And then we add 2, and then we get to here. Okay, so that's it. So which 2 are the same? So here we have a star 4, so let's rule that one out. We don't want to do that. So array sub 4, we're going to add 4. We're not going to add 8 or 2. We're just going to add 4. Okay, let's go to the next. Multibyte arrays. If we create an array of structs, it gets crazy because we can access and manipulate the elements using either indexing or pointer arithmetic. Let's see how multi-byte width structures are managed in memory. First, let's say we're working with our familiar coordinate struct. All right, so coordinate in x, in y, in z, coordinate t. we can declare an array of 3 coordinate structs like so. Coordinate t points sub 3 equals, and then we put 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have this array of 3 of them. Okay. Then we can print out the values of the second element in the array. This part has been pretty talky. This whole chapter 3 has been pretty talky so far. Not much code, but that's okay. Then we can print out the values of the second element in the array. So point sub 1.x, point sub 1.y, point sub 1.z, sure. All right, or we can use a pointer. So pointer plus 1, arrow x, pointer plus 1, arrow y, pointer plus 1, arrow z. Okay, sure. And then in the memory layout, we're going to have point sub 0.x at the start. The offset is 0. Then this one is offset by 4. This one is offset by 8. And then we get to the next struct, which is offset by 12. All right, so that's cool. That's cool. Accessing elements using pointers. Okay, so points plus 0 or address of points sub 0 points to 0x2000, so that's where we start. If we add points plus 1, or we go address of points sub 1, it points to 0x200c, next structure offset by 12 bytes. Then we offset by another 12 here. Okay, so let's consider the example. A struct stores, let's hit this potion again. A struct stores 8 integers in its ordered fields, A through H. An array stores 10 of these structs. What will be the offset in bytes from the start of the array to the 5th element's C field? Okay, so we're doing 4 bytes for an int. And there are 8 of them. So we want to offset by 32 each time. So now to get to the 5th element, we want to offset over by 128. And then we want to offset by 16 more to get to 132. All right. That wasn't correct. If we offset by, so 1 is offset by 0, 2 is offset by 32, 3 is offset by, well, I should say first. First is offset by 0, second is offset by 32, third is offset by 64, fourth is offset by 96, fifth is offset by 128, right? And then we have to offset by, so A is offset by 0, B is offset by 8, C is offset by 16. No, wait. Okay, there's where I counted wrong. A is offset by 0, B is offset by 4, sorry. Real brain dead. And C is offset by 8. So we add the 8 to the 128 to get the 136. Okay. Array casting. Let's explore a special kind of psychopathy that's possible in C. Let's assume we have this array of 3 structs where each struct holds 3 integers. Okay, so we have an array of these coordinate t's. There's 541, 732, 968. Okay, sure. Because arrays are basically just pointers, in most cases. More on that later. And we know that structs are contiguous in memory. We can cast the array of structs to an array of integers. All right, so we have this array. So if we say cast to integer pointer, then this point start becomes a pointer to integers. Then we can iterate over the known number of integers in the array of structs. Okay. So, interesting. That's fine, I guess. So far, so good. So take a look at the dump graphics function. Dump graphics, G settings. So they have an FPS, a height, and a width. So go ahead and run it in its current state. All right. So we went like 60 FPS, 1080, 1920. Okay, so far so good. Let's see. So these seem normal-ish, I suppose. And then it says we have certain values here. And so here is our 90, 1200, 1920. Okay, but then the numbers are all wrong because they're not defined. Okay. We ventured out of the bounds of our array. We're off the reservation. We're in the weeds. We're in undefined territory. This is something you do not want to do. It's one of the things that makes C powerful but dangerous. Other languages stop you from going out of bounds, but C will let you fly off the edge of the world. So let's fix the loop to only print the values that are actually in the array structs. Take a look at the graphics T struct in exercise H to figure out how large each struct is. Okay, so in this case we went 0 through 60. So we know that there are 10 here. So let's put in int, and then let's put number of ints, I guess, and then we'll say that is going to be size of graphics T, and then we'll divide that by size of, and then that'll just be size of an int. So should we just dereference the pointer? So size of graphics T divided by size of whatever's in our int pointer, and then multiply by 10 because that's the number here. And then we'll say number of ints. Now that's not exactly what it told us to do. It said to take a look here to figure out how large each struct is. So it's 3 ints. So we should say that it's 12. So let's say expecting 120. Oh, that doesn't seem right. Oh, no, hold on. It's just 3 of them. 3 times 10, so we're expecting 30. We do have the standard IO, so let's go ahead. Oh, let's go ahead and print this. So print F, and let's just put number of ints, and let's just see if we got 30 as we expect. I'm not sure the order of operations is quite right, but I think we should be fine. So let's see what we got. No, it says expected parentheses around type name. Oh, because this is graphics T. Okay, so let's do this. So it should be size of graphics T. Yeah, that makes more sense. I was mixing things up in a ridiculous way. Okay, so let's see if that's better. So it does say 30 as expected. Okay, so then let's get rid of this. Okay, so number of ints equals size of graphics T, divide size of int, and multiply by 10 because we have a 10 here. So sure. All right, I'm going to call that good. Let's go to the next one. Okay, pointer size. The size of an array depends on both the number of elements and the size of each element. An array is a contiguous block of memory where each element has a specific type and therefore a specific size. In C, pointers are always the same size because they just represent memory addresses. The size of a pointer is always determined by the architecture of the system, e.g. 32-bit or 64-bit. Let me read that. The size of a pointer is determined by the architecture of the system, e.g. 32-bit or 64-bit. A pointer's size doesn't depend on the type of data it points to, it just holds the address of a memory location. All right, so pointer example. So we have an int pointer, a char pointer, and a double pointer. So the size should never change of a pointer. It should be the same regardless. They're all the same size because they're all just 32-bit memory addresses. It doesn't matter how much memory this it doesn't matter how much memory the value at that address takes up. Okay, so array example. So we can have an int array of size 10, char array of size 10, double array of size 10. Okay, so then the size is going to be different in each case, right? Because it's 10 chars, so we only need 10 bytes. 10 ints, we require 40 bytes. 10 doubles, we require 80 bytes. So 4 for each, 1 for each, and 8 for each. So now the sizes are different because the array type keeps track of the size of each element and the number of elements. Although an array is a pointer to the first element, it's not just a pointer. It's a block of memory that holds all the elements. So it says boot dev runs C in the browser using WASM, which is typically a 32-bit system. Should we take a... Oh, interesting. What did we link to here? WebAssembly.org. Okay. If you run this code on a 64-bit system, the size of the pointers will be 8 bytes. Okay, interesting. All right, so blank have the same size on the same system, and blank may have different sizes. Okay, so pointers are always the same size, but the array size is going to be the actual size that we defined for. Okay, cool. So really, let's just go back real quick to when we first kind of saw looping through the array. So here it was like, oh, we just used 5 like kind of a magic number, right? So what we would really do here, in fact, where's the first exercise where we actually looped over an array? This one, right? So we did number of ints. So let's actually redo it based on what we just learned. So we know that if we do here, so it'll be len g settings equals size of g settings divided by size of no. Oh yeah. Size of graphics t, right? Now, of course, we're trying to loop through 3 ints for each g settings. But here we could go 3 times len g settings, basically, right? And that would still be fine, I think. Oh, wait. No, I didn't get it. Okay, so size of g settings divide by size of graphics t. Oh, I didn't get anything. Huh. Okay, let's see. So for int I equals 0, I is less than 3 times len g settings. Okay, so let's see. Printf. It says 0. Okay, so that's not right. Okay, so So let's put size of G settings, size of graphics T, (4 and 12). Size of G settings came in at 4. Okay, so I clearly overlooked something that they explained to us here somewhere, I think. No, what was it? Okay, so, oh, ZU? Wait, what is ZU? Did they tell us that? Oh no. What is ZU? Oh no, where is it? Okay, so C standard IO. Unsigned decimal integer. What is the Z? What is the Z? Oh, here it is. Length Z. Huh. Okay, I still might have screwed something obvious up. Let's see. So size of G settings. No, hold on. So they say int array. And then they say size of int array. So they say ZU. So let's try ZU instead. Nope, it still says 4120. Okay. Graphics T array G settings 4. Huh. Okay. So if it were like, I don't know, let's just say that we have a void check int array size, and it takes a int a array of 10, I guess, and then we printf and put ZU new line, and then we put size of A, and then we call that here. And then we pass in an array here, which is going to be just like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, maybe? Can we do that? I think that's not correct. I think we have to go. Let's see, warning. Size of on array function parameter will return size of int star instead of int 10. Okay, so that's a good warning. And similarly, size of G settings will return the size of the pointer, not the array itself. Okay, so we can't do that the way I hoped, which is nice to see it confirmed by the warning here, I guess. Okay, so let's not do this. So here we'll just say int a 10. So now it says size of an array. Okay, so we still get the same warning. error expected 08. Okay, so here it came out as 40, but if it came in like this, then we can't do that. Well, that's a little disappointing, but hey, whatever. We'll just have to live with it. Okay, so let's go back here. All right, so pointers, same size, array may have different sizes. But I hoped that that would account for an array passed in. I think that's what this next lesson is actually about to tell us, though. Arrays decay to pointers. We would have learned it if we'd just gone on to the next lesson. All right, well, we're doing it now. So we know that arrays are like pointers, but they're not exactly the same. Arrays allocate memory for all their elements, whereas pointers just hold the address of a memory location. In many contexts, arrays decay to pointers. Okay, so this is... Where are we? Port70.net. It's an ISO document? Okay. Fair enough, fair enough. Meaning the array name becomes just, quote unquote, just a pointer to the first element of the array. So when do arrays decay? So arrays decay when used in expressions containing pointers. So in this expression, array decays to int star, and also here. And also when they're passed to functions. Okay, so that's what we just learned. So they actually decay quite often in practice. Damn, that's sad. All right, so that's why you can't pass an array to a function by value like you do with a struct. Instead, the array name decays to a pointer. Okay, so when arrays don't decay? Sizeof operator returns the size of the entire array, e.g. size of R, not just the size of a pointer. But as we found out, if it's decayed already, then you're SOL. AND operator, taking the address of an array with AND array gives you a pointer to the whole array, not just the first element. The type of AND array is a pointer to the array type, e.g. int star and then 5 for an int array with 5 elements. So initialization, when an array is declared and initialized, it is fully allocated in memory and does not decay to a pointer. Okay, great. So let's take a look at the main function. Here we are. So it declares an array of numbers, core utilization that represents the CPU utilization of each core on a system running the SnekObjects interpreter. The array has 8 elements, okay? So on lines 12 and 13, it prints the size of the array and the length of the array. Okay, size of the array and the length of the array. Okay, so here they did what I tried to do before, and in this case it does work because we just declared it hasn't decayed. Okay, great. So complete the core utils func to print size of core utilization in a core utils func x. Let's just copy this. Okay. And then x is the size of the array calculated using the sizeof operator. Notice that due to the array decaying to a pointer, the reported size is the size of a pointer, not the size of the actual array. Well, this is what we learned. Not the hard way exactly, but a harder way than this. Anyway, it's fine. So let's just put ZU here, okay, and we'll put size of, and then we'll put core utilization, okay. Oh, had content that was not flushed. So is that a warning about this? Oh, okay. Notice that due to the array decaying to a pointer, the reported size is 4, not the size of the actual array, which would be 32. Okay. Well, now we've had that beaten into our heads. Let's go to the next. C strings. So since the beginning of the course, we've been doing these shenanigans. We've been doing these shenanigans to be able to print strings. So the char star message equals SSH terminal.shop for the best coffee. So I told you not to worry about the weird char star syntax, but now that we understand a bit about pointers, let's dive into it. In the example above, message is a pointer to the first character of the string, SSH terminal.shop for the best coffee, which is a C string. C strings are how we represent text in C programs. Any number of characters, chars, terminated by a null character, \0. Nice. And let's see, it's a pointer to the first element of a character array. Okay, cool. So it's important to understand that most string manipulation in C is done using pointers to move around the array, and the null terminator is critical for determining the end of the string. In the example above, the string SSH terminal.shop for the best coffee is stored in memory as an array of characters, and the null terminator, \0, is automatically added at the end. Awesome. So C strings are simple, so unlike other programming languages, C strings do not store their length. The length of a C string is determined by the position of the null terminator, \0. Functions like strlen, which we have here from the string.h header. So this one is, it calculates the length of a string by iterating through the characters until the null terminator is encountered. And this lack of length storage requires careful management to avoid issues such as buffer overflows and off-by-one errors during string operations. Okay. It's kind of messed up, man. Kind of messed up. All right, I'm sure it's fine. So you can declare strings in C using either arrays or pointers. All right, so in this case, we used the different syntax. We put the brackets after. But it's the same difference either way. So it says hi sneak. Okay. The output is the same. Let's break down the memory of this example. Okay. So let's say we have an H, it takes up just 1 byte. We have an I, it takes up just 1 byte. And then, not shown, we have a null terminator, which takes up 1 more byte. And then in this one, we have the S, that's 1, the N, that's 1, the E, that's 1, and the K, that's 1. So we should have 3 bytes here, including our null terminator, and 5 here, again including our null terminator. And then once we format here, so we make a replacement, and this becomes the hi, and this becomes the snake. Now I'm assuming that when we do this replacement, we probably don't put a null character in there. Let's break down. So we aren't using all 50 characters. So in this case, we declared it with a length of 50, but like we didn't use all 50. So presumably we're going to have the SNEK, then we're going to have a null terminator, and then the rest, I don't know, they could be anything, I suppose. Let's see if they tell us anything more. So we have a string cat function, string cat first second. So this should mash these guys together. It appends its second argument to the first argument. In this case, it appends lang to snake. So we get the output, hello, snake lang. Oh wait, is this an error? Because it was a big L here. Why did it turn to a small L? I'm going to assume that's an error. Here's what first might... I'm going to assume that's an error unless it says otherwise. So first might be SNEK, null terminator, and then God knows what until we get to the end. Okay, fair enough, fair enough. Note, there is a bunch of garbage memory after the end of the string. Okay, so that's what this represents. 4 hooks for garbage memory. So here's what second might look in memory. So lang bang null. Okay. Oh, so then after string cat, let's take a look. SNEK lang bang null, and then a whole bunch. A whole bunch. Okay, that's crazy. Actually, that's not what I expected. We still ended up with a whole bunch there. So why is that? First was like this. So the string cat function appends the string lang to the end of the string snek, but smartly uses the null terminator to know where to start appending. It doesn't know the length of the string, but it knows where it ends. But we still end up with a length 50 of the array. Okay, because it's a in-place type modification. So what if we didn't have enough room? What if we did it like this, and then did string cat first second? Can we just try that here somewhere? Oh, this one is difficulty 8. Interesting. I wonder what makes this one a difficulty 8. I guess we're about to find out. Okay. So we got these string pointers. Okay, we're going to do some a little experimentation, but let's go ahead and finish the exercise first. Okay, so in SnekLang, we have a bit of not invented here culture. Oh, really? So as such, we've decided to implement our own string concatenation function. So we have to complete the concat strings function. It should append string 2 to the end of string 1 in a place. Okay, so here are the steps. Okay, so 1, find the null terminator of string 1. 2, iterate over string 2 and copy each character to the memory locations at the end of string 1. 3, add a null terminator at the end of the concatenated string. Hey, reminder, don't cheat and use string cat. And string 1 is already allocated with enough memory to hold the concatenated string, so don't worry about that. Don't worry about that yet. I don't know if we'll worry about that, but let's see what we're going to do here. So let's do, here, let's copy these steps into here so that we can see exactly what we're doing. Okay, so this will be this one. And then this will be this one. Okay. All right. So step 1, find the null terminator of string 1. So we're going to say for int I equals 0, I. So we'll say string 1 sub I is not equal to null, right? I plus plus. So interestingly, we don't actually need to do anything in there. We just need to find what where the I belongs, right? So let's make it a while instead then. So we'll say int null terminator 1 equals 0 while not equal null, and then we'll say right? Okay, so that will find it. Is that how we want to find it? I say yes. Okay, iterate over string 2 and copy each character. You know what? Honestly, I am just going to call it I. Oh, here I misspelled it anyway. Okay, let's just call it I. I equals 0, string 1 sub I is not null, I plus plus. Okay, cool. Null char. Sure, so iterate over string 2, copy each character. So in this case, I guess I'm going to call it J, or am I? Yeah, let's just call it J. So we'll say for int I, or int J, I just said J, J's, so we'll say string 2 sub J not equal null. j plus plus, right? And then we'll say string 1 sub plus plus I equals string 2 sub j. Is that what we want to do? So we'll iterate. No, that's not what we want to do. We want to do I plus plus because we want to overwrite that original null, right? So the first time we'll overwrite the null and then we'll increment it so that we keep going. Fair enough so far, I guess. So then add a null terminator at the end of the concatenated string. So here, so we went j plus plus. So then, wait a minute. So we still want the j afterwards. So I'm just going to say int j equals 0 here, and just get rid of it here. So then at the end, we'll say string 1 sub j equals. Okay, so it's void concat string. Oh, let's see if that's right. Nope. Oh, I put string when it should have been string 2. Okay. Nope. It was... Oh, it didn't work. Okay, so this is a difficulty 8. Imagine what the difficulty 10s are going to look like in this one. I don't know. I think it's fine. So, let's see. So, int I equals 0. So while string sub I is not null terminator, I plus plus. Oh, should not change the original string. Find the null terminator. Copy each character to the memory locations at the end of string 1. Oh, shoot. Okay, I'm going to make this one also a while. I'm going to put plus plus here. String 2 sub j. I don't think that quite fixes it yet, but I think it's maybe closer. Okay, so I still ended up making the string 1 empty, so we don't want to do that. Don't want to do that. Okay, so let's go ahead and hash include standard IO h, and let's print f. So it's while string sub j not equal. So let's print f, and let's show both strings at the start, right? Okay, so it showed hello world here. Let's put a new line at the front. So it showed hello world. Just put 2 new lines. So this shouldn't have changed anything. So while string 2 sub j is not null, string 1 sub I plus plus equals string 2 sub j plus plus. Okay. So let's print f the same thing at the end. Okay. Well, here, yeah, here it looks like hello world and still hello world, but it looks like the null thing. Wait. Why is there an extra space here? I don't know about that. Concatenating an empty string to a non-empty string should not change the original string. Empty and non-empty? Let's see. So this one was hello, and then it was empty string here. Okay, so this is an edge case that I didn't consider. It was telling me that exact thing this whole time, but I was in the weeds, I guess. All right, it's fine. So, concatenating an empty string to a non-empty string should not change the original string. Okay. So in this case, I guess we would have skipped right over this because it would have been null if it was an empty string, I think. Does it say something about the empty string here? I think the empty string should just be a null character, but I'm not sure. Yeah, it should just be a null character. So we should skip over this. Then, okay, well, there's the mistake. Took me a while to see it. It should be I at this point, I believe. Yeah, okay. That was a simple error, and man, so illogical. Okay, so it says okay now, so now let's see if there's some other ones. So, concat empty, non-empty, or let's see, empty to non-empty. This is a longer string that will be concatenated with another long string. Okay, I don't think the length matters much, at least according to the way I did it. String to an empty should change the original string. I think we're good. All right. Oh, damn, I didn't have the potion. That's very sad. It didn't even look like it paid out that much either. Okay, I'm going to look at this next one, but I'm going to take another quick 2-minute break before I go into the C string library. Be right back. Wait. Be right back. Meelp, this is sure going to take a while if I keep making simple errors, but whatever. If it takes a while, it takes a while. So, let's go to the next thing. C string library. The C standard library provides a comprehensive set of functions to manipulate strings in the string.h header file. Here are some of the most commonly used functions. Uh-oh. This one's a difficulty 10. No! There's a lot more in here, too. That's crazy. All right, we're going to keep going. The C standard library provides a comprehensive set of functions to manipulate strings in the string.h header file. Here are some of the most commonly used functions. String copy copies a string to another. Okay. String copy destination to source. Destination now contains hello. Okay. I guess that works. String cat concatenates, appends one string to another. All right, so destination. So we got to leave enough room, it looks like, right? Oh yeah, this is what I was talking about, trying to experiment with the... I was trying to think of experimenting with some of these in the other one, but I don't know if I'm going to get to it. Let me check my sound, make sure it still seems kosher. The music does seem a bit loud, actually. Let's see if I can turn the music down a little bit. Let me just turn that down a tad. Okay, let me check again. Oh, it can go down more. Okay, now let's see. Okay, now let's see. That's a little better. All right. Sorry, just checking. Okay. Let's do string cat concatenates. So now we can turn hello and world with a space here into hello world. Okay. So string length returns the length of a string excluding the null terminator, mind you. So we get 5 here. String compare compares two strings lexicographically. Lexicographically. So if we do string compare string 1 and string 2, then hello will be sorted before world, so result is negative. String n copy copies a specified number of characters from one string to another. Okay, so if we have hello, and then we have a destination with 6, and we copy 3, it contains just hell. All right, fair enough. Ensure null termination. Uh-oh. Okay. String n cat concatenates a specified numbers of characters from one string to another. So we have hello and world, but this time we only copy 3 characters over. So 1, 2, 3. Hello, whoa. Okay. String char finds the first occurrence of a character in a string. Okay. So where's the L? Pause points to the first L in hello. Oh, so it turns into a pointer. Okay. String finds the first occurrence of a substring in a string. So it's hello world, we do position of world, and now this becomes, again, a pointer. Okay. So complete the smart append function. Okay, so the last one we did was concat strings, but now we're going to say smart append, which we're using this text buffer type, apparently. So it has a char buffer of 64 and a size t length. All right. So what do we do in the smart append? Append a source string to a dest text buffer struct. It's called a smart append because the destination buffer is a fixed 64 bytes and it checks for available space before appending, appends as much as possible if there's not enough space, always ensures the buffer remains null terminated, returns a status indicating whether the full append was possible. Okay, cool. So here are the steps. Okay, this whole series of steps. This one's listed as difficulty 10, but if they give us like all the steps, how difficult can it be? We're about to find out. If either input is null, return 1 false. Okay, so if dest, okay, if, here we go, dest equals null, or source equals null, return 1. Okay. Create a constant to represent the max buffer size of 64. So const int max buffer size equals 64. Okay. Here, and we can even check them off. How hard can we're gonna see how hard it can be. Get the length of the source string using string length. Okay, so it should be an int, I guess, string length. Oh no, it's a size t. Okay. Size t len equals string length source. Okay. And then calculate the remaining space in the dest buffer. Notice that it stores its own length. Don't forget to account for the null terminator. It doesn't count as part of the length. Okay, so it has a length in there already. So let's see. If the source string is larger than the remaining space, so we're going to say if len plus 1 for the null terminator is greater than, and then this will be the length. So we'll take the max buffer size minus the length, I guess, right? Max buffer size minus dest length, right? Okay. So then, so if the source string is larger, then copy as much of the source string as possible to the dest buffer using string ncat. Okay, so we'll say string ncat, and in the example that was shown, we saw that we just do it. So destination, source, and the number. So we need this number, right? So we need like the available space. So let's say int available space equals max buffer size, right? Subtract destination length. Okay, so then we'll use that here. Available space. Okay. But we want to, do we want to subtract 1 for the null terminator? I think so. Let me just think for a second. I think that at this point we want to subtract 1 for the null terminator. So we'll go strncat. Whoops. So the destination is going to be our dest buffer. Is buffer what it was called? Buffer. Buffer. And the source will be the source. Okay. And then we'll put available space, subtract 1 for the null terminator. And then, so then we'll say dest length equals max buffer size. And then we will, okay, so we are going to put the null terminator on. So then we'll say So what we did here in string ncat, wait a minute, concatenates a specified number of characters from one string to another. So do we think that this one will handle the null terminator? Let's see what it says. Appends at most count characters from the character array pointed to by source, stopping if the null character is found, to the end of the null terminated byte string pointed to by dest. The terminating null character is always appended in the end. Okay. So the maximum number of bytes the function may write is count plus 1. Okay, works for me. All right, so yeah, so we updated that. Whoops. And then we return 1. Okay, so then else append the entire source string to the dest buffer using string cat. So we'll do string cat dest buffer source, right? And so in the example, we just do string cat and that's it. So then we'll update the dest buffer length. So we will put dest length plus equals len, right? Yeah, that's right. And then return 0 true to indicate the full append was possible. Okay, I'm nervous, but let's try running it real quick. This one is a difficulty 10, it says. Okay, well, it says 2 of 2 tests successful, 2 tests skipped. Oh, no. Okay. So return, wait. Okay, so the run tests are these ones. Should return 1 for null value. Okay, we got that. So in this case, we did nothing and then hello, and then we were like, should return 0. Okay. Buffer should contain hello. Okay. Length should be 5. Okay, okay. So we're moving in the right direction, but we didn't run this test. This is a very long string that will fill up the entire buffer. Should return 1 for unsuccessful append. Okay, so let's do this one and let's see what it returns. Whoops. I didn't mean to do that. Okay. So we're gonna go. So in main, oh, we can't edit this. Oh, we can't edit this. Oh, interesting. All right. I'm just gonna copy this over into here, I guess. No, that's not gonna work. Let me think for a sec. Okay, let me just look it over. So we know that this one is going to be more than the available space. Okay. If length plus 1 is greater than available space, then we string cat to the available space, subtracting 1, which I think matches up with what was said in the doc, right? So it says the maximum number of bytes the function may write is count plus 1. So that's why we can't do the full available space, we have to subtract 1. Right? That seems to match up with what was said here. And then we return 1 here, which is what was asked for, right, in the main. So return 1. and then it should say length should be 63 after overflow append. I don't think that's going to be correct. So I put it to max buffer size, and that is not right. It should just be plus equals len, same as here. So we went update the dest buffer length to the max size. I think maybe we're good now. Let me run this again. I think it's going to fail somewhere, and I'm going to be kicking myself. Okay, so in the last one, wait. Oh, this one, wait. Okay, so this is a very long string that will fill up the entire buffer, and then extra should return 1. So buffer should remain unchanged in that case. So do we think it will remain unchanged? Yeah, because this is going to be... This available space is going to... This is going to be 0. Oh, shoot. I think it's fine. If anything, it'll just replace the null terminator with another one. I think it's gonna mess up. So this is a long string that will fill the whole buffer and leave no space for some of the chars. So filled to capacity, result equals 0. Okay, I'm gonna try running it. Here we go. Hey, it might work. I should hit the potion again though. Nope, it didn't work. No big surprise there. So I got 69. Length should remain 63. Okay, yeah. I just looked at that, and yeah, that was not right. So it should be... So in this case, we should add available space -1, which is what we... It seems kind of obvious now that I've seen the error, but it sure didn't before I saw the error. That's because I'm kind of dumb. All right, let's hit it again. Okay, let's go to the next. Forward declaration. Sometimes you have a struct that may need to reference itself or be used recursively. For example, consider a node struct that can contain other nodes. This might be useful for building a linked list or a tree. Okay, so we have a node, it has a value, and then it has a next. Okay, so that's a linked list. So the problem here is that node t is not defined yet, so the compiler will complain. To fix this, we can add a forward declaration, right? So note that the forward declaration must match the eventual definition, so you can't do something like this. So in this case, it's fine. Struct node, node t, struct node, node t. But in this case, we did struct node, node t, and struct bad name node t, and so it wasn't allowed. All right, sure. Oh, this is an easy one. Oh, it's only difficulty 4, yay. Snakelang, like Python, is built on the idea of dynamic objects, and objects need to be able to store other objects. So run the code in its current state. Notice that the H file is producing an error because the object struct references itself. Fix it with a forward definition. Okay, so we'll just add a forward definition right here, right? Just like they just showed us. And like literally all we do is just put this here, right? But this time we just say this, right? I mean, that's it, right? We put SnekObject t. I guess that's all we need, baby. Okay, so next, I'm going to hit the potion before this next one. So forward declarations can also be used when two structs reference each other, a circular reference. For example, a person has a computer and a computer has a person. Okay, so typedef struct computer, computer t, person, person t, sure. So complete the definitions of the employee and department structs. Okay. So that we have circular reference. A person can have a computer, and a computer can have an owner. Sure. Okay, so we're just going to fill this in here. So we'll have typedef. Wait a minute. Complete the definitions, and then look at the implementations in the C file to understand how they should be defined. Okay. All right, sure. So, I mean, seems simple enough, kinda. So we have an employee T. So we have int, wait. So int char star, and the department is a department. Okay. Char star name, and then department T. So if it's null, I guess this is a pointer as well. Okay, so this will be employee T, and this will be department T. And then the department itself, we can see it has a name and a manager. And the manager itself is an employee T. So employee T manager. And then here, char star name. Okay, does that match up? I think so. This should be a pretty easy one, so I think we're almost done. So then we are going to put typedef struct employee T, and typedef struct department T. Feels like a pretty familiar example from school, kinda. So typedef struct employee. Wait a minute. Okay, typedef struct employee. Oh, this is typedef as well. My bad. Okay, so it says successful. Let's see what was skipped. I think we're good on this one. It's an easy one, right? Yeah. Let's just... Oh, wait, let's hit a potion first. Oh, yeah. Okay, here we go, baby. Here we go. Submit. And good. Next. Enums, unlike Golang, a language living in 1970, C has explicit support for enums enumerations with the enum keyword. Lane says TJ is salty because Go is a simple modern language that companies actually use to ship products. What? Not all programming languages can be academic thought experiments like OCaml? Okay. Well, fair enough. You can define a new enum type like this. Typedef enum days of week. Monday, taco, Tuesday, Wednesday, Thursday, Friday, Saturday, fun day. Okay, sure. Days of week T. So the typedef and its alias days of week T are optional, but like with structs, they make the enum easier to use. In the example above, days of week T is a new type that can only have one of the values defined in the enum. Monday is 0, taco Tuesday is 1, Wednesday is 2, Thursday 3, Friday 4, Saturday 5, and fun day 6. You can use the enum type like this. So we can do days of week T day, or if you don't want to use the alias, enum days of week day. Okay, so there we go. So an enum is not a collection type like a struct or an array. It's just a list of integers, just a list of integers constrained to a new type where each is given an explicit name. So the snakelang graphics library needs to represent colors. Okay, this is a difficulty 3. All right. So create a color enum and the color t typedef with red, green, and blue values in that order. Okay, so we'll go typedef, we'll put enum, we'll put color, and then we'll put a list, and it will say red, it will say green, it will say blue, all right, and then it will say color T, and then does that match what we did here, basically? We had a trailing comma. All right. Okay, let's move on to the next. Getting that potion XP, baby. Okay, so non-default values. Sometimes you don't just want to enumerate some names where the underlying integer constant values don't really matter. You want to set those enumerations to specific values. For example, you might want to define a program's exit status codes. So an exit success is 0, an exit failure is 1, and an exit command not found is 127. Okay, so alternatively, you can define the first value and let the compiler fill in the rest, incrementing by 1. So 200, 201, and 202 for lane WPM, prime WPM, teach WPM. Okay, so update your color enum to the following values, 55, 176, and 38. All right, I don't know why there are actually these numbers, I don't think. But whatever, all right. Uh-oh. Why is this one listed as difficulty 8? I'm freaking out. That doesn't seem right. What? Wait, hold on. What? Okay, Envim green? I don't know, man. This seems crazy. So assert that 55, 176, and 38 not defined as 0, 120, 215. Why is it difficulty 8? That seems crazy. All right, let's see what happens. I don't know. It's a mystery to me, baby. So one of the best features of enums is that it can be used in switch statements. Enums plus switch statements avoid magic numbers, use descriptive names, and with modern tooling, it will give you an error or warning that you haven't handled all the cases in your switch. So here's an example. So for the switch log level, you can do a case log debug, a case log info, a case log warn, and a case log error, or an unknown log level. Okay, so we have a break after each case, so if you don't have a break, the next case will still execute. So the fall through is the default behavior on this switch. So many devs have written bugs when using switch statements because they forgot to add break. Okay, sure. So in some rare cases, you might want the fall through. So here we just list out some cases. Minor error. 4 and 5, major error. Usually it's a foot gun. You'll almost always want a break at the end of each case statement. Fair enough, fair enough. So complete the HTTP to string function. Given the enum defined in HTTPH, so here we go, we've got these. Probably want to copy those. So given the enum defined in HTTPH, it should return a hard-coded string with the human-readable version of the HTTP status code. Okay. So we'll go switch, and we put in the code. So far, so good. Then let's paste these in. Whoops. So these are going to be our cases, right? Case. We don't want this. Okay. So that's a case. We'll want the break, of course. Talk about slow typing, my goodness. Gotta get better, I guess. Then we'll want a default. And then we need to put these things. So we will copy that. Oh wait, we don't need a break. We're just gonna return. So what the heck am I doing? Crazy, crazy, crazy. All right. Okay, 401 unauthorized. Not found. Okay. Sure, sure. Gotta make sure we handle the most important ones first, as we well know. Okay. And this one. Oh, gosh. Unknown HTTP status code. Okay. Whoops, I have a colon. Okay, so the default, so we should have the default ready to go, I guess. I think that all seems fine, and this is still going? All right. Okay, let's go to the next. Sizeof. The same sizeof operator that we've talked about works on enums. Generally, enums in C are the same size as an int. However, if an enum value exceeds the range of an int, the C compiler will use a larger integer type to accommodate the value, such as an unsigned int or a long. So an unsigned int doesn't represent negative numbers, so it can represent larger positive numbers. A long is just a larger integer type than int, so it can represent larger numbers. Nice. So enums are often used to represent the possibilities in a set. For example, small, medium, large, extra large. Your code probably cares a lot about which size a variable represents, but it probably doesn't care that small happens to be 0 under the hood. From the compiler's perspective, enums are just fancy integers. Okay. At the start of main, print the size of the two enums defined in main C. In the format, the size of big numbers is y bytes. The size of HTTP error code is x bytes. And remember, ZU is the format specifier for size T. Okay, cool. So we will totally put that in here. So let's just copy these. And we will totally go printf. We'll put our stuff in here. This will become a new line. This will become %ZU. And this will become a %ZU. And then we'll say size of, and we'll put big numbers, and we'll put size of, and we will put HTTP error code, right? Something like that. No, okay, I left out the I left out the trailing new line. I stuttered on that one. Okay, so let's send that. How's that? Does that work for us? Okay, let's go. Oh, another chest. Nice, nice. Pretty generous with these. Okay, let's go to the next. Union. So now that we understand structs and enums, we can learn about unions, a combination of the two concepts. So this is not the kind of union that 300K earning Google employees fight for because they are underpaid and don't have enough oat milk in the office kitchen. No, this feature is one that even Golang doesn't have, probably because they were worried about getting fired from Google for just mentioning the word. Unions in C can hold one of several types. They're like a less strict sum type from the world of functional programming. So here's an example union. So typedef union, age or name. So it could be an age int, or it could be a char star name. Nice. So the age or name T type can hold either an int or a char star, but not both at the same time. That would be a struct. So we provide the list of possible types so that the C compiler knows the maximum potential memory requirement and can account for that. So this is how the union is used. So age or name T lane, we can put age equals 29 and then print the age here. So here's where it gets interesting. What happens if we try to access the name field even though we set the age field? We get nothing? Well, to be more specific, we get undefined behavior. A union only reserves enough space to hold the largest type in the union, and then all of the fields use the same memory. So when we set age to 29, we are writing the integer representation of 29 to the memory of the lane union. Okay, so here it is, 29, sure. Then, if we try to access name, we read from the same block of memory, but try to interpret the bytes as a char pointer, which is why we get garbage, which is interpreted as nothing in this case. But put simply, setting the value of age overwrites the value of name and vice versa, and you should only access the field that you set. Wild. Wild, wild, wild. Interesting. So that sounds like, doesn't sound like we could use this in a lot of situations, but we'll see, we'll see. So snakelaying is going to need objects. We'll hand code those objects, and snakelaying developers will use them to store dynamic variables, kind of like Python. Everything is an object, even simple integers and strings. Okay, so take a look at the SnekObject struct in exercise H. Okay, so here is our SnekObject. It has a kind, and it has a data, and that's it. Okay, cool. So it looks like we still need to define the kind, right? Because that is not here. It looks like it's going to be here probably. Okay, so create a SnekObject kind T enum type in exercise H. It's the one used as the kind field of the provided SnekObject. It's an enum that can be an integer or a string. All right, cool. So we'll totally do that. Yeah, that's our first step. So here we go. So we'll typedef enum kind, let's say SnekObject kind. All right. Integer string, and that is SnekObject kind T, okay, and then complete the format object function in exercise C. That uses a switch on the kind of a SnekObject T and writes a formatted string to the associated buffer. Okay, so this is an enum. So we went over the union, but are we not actually using the union in the assignment? Kind of makes sense because they didn't make the union sound like something we'd be able to use very much, really. So I guess that's cool. struct. So this is a union. So, okay, so the data is one of those. Interesting. So the union was already defined for us. For some reason, I thought we were going to have to define a union. Okay. So we're totally using it, I might be losing it, man. All right, so exercise C. We will learn how to copy this data later. So kind, so new string, has a kind and it has a data. Okay, so here we will totally go like format object and let's see. Use a switch. Okay, so we'll switch and we'll pass in the object kind. Sure. And then we'll do a case. And the first case is integer. And the second case is string. And I don't know if we'll use a default, but okay. And what else? So we can't really use a default, right? So let's get rid of the default then for now. So for case integer, write int n to the buffer, replacing n with the integer value. Okay. You can use sprintf to write the formatted string to the buffer. Okay, so let's try sprintf, and we will put int, and we'll put a d. And do we need a new line here? I think not. So then we'll put in the object.data here. All right, I guess. And then in this case, we will put sprintf, and we will put string, and then we will put %s, and likewise is object data here, so we can try running that. So we missed out on here. So passing SnekObject t to parameter of incompatible type const char star. Interesting. So sprintf to write the formatted string. Let's take a look. So it's union SnekObject data. We tried to pass this, but it didn't work. There was no luck. Write formatted data to string. Composes a string with the same text that would be printed if format was used on printf, but instead of being printed, the content is stored as a C string in the buffer pointed by string. Okay, so we put the buffer in here. Totally left that out. So the buffer is first, right? Okay, so int 5. Okay, so I didn't get the right number here. Assertion failed. Oh, interesting. So I got 64508. Messed up. $64,508. Well, that doesn't seem right. Okay. So don't touch below this line. We won't worry about that. We did integer and string, but did I put the right numbers? Integer 0 and string 1. Let's just go ahead and put those. I think it might start with 1. Okay, let's try again. Nope. Nope, that didn't help. Okay, so case integer. So void format object. So do we actually put the dot and put okay, I don't know what I'm doing right now. String? Oh, gosh. Okay, one sec. Okay. All right, let's go to the next. Okay, so now we know kind of how to use the union, which I obviously didn't at first. Okay, so memory layout. Unions store their value in the same memory location no matter which field or type is actively being used. That means that accessing any field apart from the one you set is generally a bad idea. Okay, so we're re-emphasizing this. It's clearly important. Take a look at the val or ART union. It represents either an integer value or an unassigned, non-negative integer error code. So run the code in its current state. Notice that the value field is set to -420. Then the data in each field is printed. The value field works as you'd expect. Okay, so we set to 420 here. Fine. So then we put this value out. So then we try to put this error out as something or other, but it came out as this guy. So that's messed up. So the value field works as you'd expect, printing -420. However, the error field prints the large number. So it's trying to interpret the bytes of -420 as an unsigned integer, which results in a very large number. So uncomment the next block of code and run it without submitting. Okay. So notice that we now set the error field, an unsigned integer, to uint_max, which is a constant representing the largest possible unsigned integer. Okay, so here it is. And then as expected, the error field prints this large number. Okay, so however, the value field prints -1. Pretty messed up. It's interpreting the bytes that represent this large number as an unsigned integer as a signed integer, which is -1. Man, I'm a mess. So, submit the fully uncommented code. Okay, sure. Let's move on, baby. Okay. So unions, union size. A downside of unions is that the size of the union is the size of the largest field in the union. So take this example. So we have int or error message. So we could have a data, or we could have an error string, which we set to the size 256. So this int or error message union is designed to hold an int 99% of the time. However, when the program encounters an error, instead of storing an integer here, it will store an error message. The trouble is that it's incredibly inefficient because it allocates 256 bytes for every int that it stores, all right? So if we imagine that an array of 1,000 int or error message t objects, so even if none of them makes use of the error field, the array will take up 256 times 1,000, so 256,000 bytes of memory. An array of ints would have only taken 4,000 bytes, assuming 32-bit integers. Okay, so we're going to have to look at these quiz examples. So if the size of an int is 4, size of char is 1, and size of long int is 8, and we make this union, but these are all long ints, okay? So how many bytes will an instance of sensor data require? So 8, right? Okay, it looks like there's a question on each of these probably. Okay, next. So which is the correct order from least to greatest of the memory requirements of the of the given unions? So sensor data we said was 8. So this union could be 256. Let's see here. Unsigned char. So an unsigned char is same thing, right? 256. But it could be this struct image data. So this one's larger right off the bat. Oh gosh. So 256, 256. This struct has 1024 in it, plus the width and height. So it's clearly larger than the sensor data. The sensor data is 8. The packet payload is the size of the image data, which is going to be 1024 plus 16. So 1040. And then this one has these different structs. Okay, so this one has 2, so that's 8, same as sensor data. This one is 8. So this one is 8. So let's see. So sensor data and item, I think, are the same. So they have structs that are 8. Right? So the greatest is packet payload. So we can answer that. But I think sensor data is 8. And it looks like item should also be 8, right? This one's 8. This one's 8. This one's just 4, but 8 is the largest. Okay, let's look again. Oh, that's it. So one interesting, albeit not commonly used trick is to use unions to create helpers for accessing different parts of a piece of memory. Consider the following. Okay. So we have a typedef union color struct. So uint 8t are all these 4 components. All right. So then we have RGBA listed as uint 32t. So these are the same size, I guess, right? So this is 8, 8, 8, 8, and this one is 32. So I guess that's fine. So unlike in 99% of scenarios, it makes sense to both set and get values from this union through both the components and RGBA fields. So both fields in the union are exactly 32 bits in size, which means that we can safely, access the entire set of colors through the RGBA field, or get a single color component through the components field, okay? So the convenience of additional fields with the efficiency of a single memory location and the fragility of C, he says. So Snakeling has support for networking. So complete the packet header union. So we have a TCP header struct. So let's do similar to what we saw here. So we'll put struct, and this struct has 2 things in it, it said. The first 2 bytes are the source port, the next 2 bytes are the destination port, and the last 4 bytes are the sequence number. Okay. So then this is called TCP header. And then the other item in the other way to access the packet header is as raw. And so the raw is going to be long, or actually let's go uint. Let's see. So we can do 1, 2, 4, or if it's 8 bytes, Should we just do 2 of these? Let's see. Raw, an array of 8 bytes. Okay. So we'll do uint 8t, 8 of them, and we'll call that raw, right? And then here in the struct, we're going to have 2 bytes. So uint 16t, which are source port. Then we're going to have uint 16t for dest port. And then we're going to have uint 32t for sequence number. Oh gosh, sequence number. Okay. Okay, didn't quite get that right. Uint 8t raw to declare an array place after. Okay, okay. I've seen that several times, but just brain farted it. Slipped my mind. Okay, so that's cool. Let's go to the next. Uh-oh, I need another potion again already. The stack. So remember how I told you that memory is basically just a giant array of bytes with addresses at various offsets? So that's true, but it also has some additional structure. So in particular, memory is divided into 2 main regions, the stack and the heap. We'll cover the heap later. The stack is where local variables are stored. When a function is called, a new stack frame is created in memory to store the function's parameters and local variables. When the function returns, its entire stack frame is deallocated. The stack is aptly named. It is a stack, the last in, first out data structure, of memory frames. Each time a function is called, a new frame is pushed onto the stack. So when the function returns, its frame is popped off the stack. So take a look at this example function. So the void create typist uses envim. Int wpm equals 150, char name equals teach. Okay, so say we call create typist, okay? Before the call, our stack memory might look like this, with the next memory address to be used, 0xFEFC. So this is the next one to be used, I guess. Higher address is over here. So once called, the stack pointer is moved to make room for the return address to pick up execution after the function returns, okay? Arguments to the function, local variables in the function body. Okay. Making progress, making progress. I guess this is like close to a halfway point, kinda, so that's not too bad actually. The local variables are stored in the stack frame. Okay, so int uses envim, so we did 1 for that. And then wpm, teej, so these are all on the stack frame. So when the function returns, the stack frame is deallocated by resetting the stack pointer to where the frame began. Okay, so we'll run in the current state. And let's see, so the pointer offset was like this, so let's take a look. Print stack pointer diff. So we were looking at a built-in frame address. I guess we'll need to look at the tip here, but let's not look at it just yet. So the memory addresses allocate more and more space. Okay, cool. So we print message 1, print message 2, print message 3. Okay, cool. Update where print message 2 and print message 3 are called from so that all 3 of the functions use the same stack space. Okay, so let's go ahead and do that. So we'll move this up. Just like that. Is that all we want? Yeah, that's pretty much it. Okay, so the print message functions should not call each other because that creates a new stack frame on top of the existing one. They should be called sequentially from the main function. Okay, let's go to the next. So why a stack? Allocating memory on the stack is preferred when possible because the stack is faster and simpler than the heap, which we'll get to. Be patient. So efficient pointer management. Stack allocation. Oh, you're on the daily leaderboard? No way, really? Let's take a look. Okay, that's not a lot. Looks like today's daily leaderboard is actually quite low. 50K for the leader. And I'm only halfway through. I might pass the leader. That'd be cool. Anyway. That's fine. So, efficient pointer management. Stack allocation is just a quick increment or decrement of the stack pointer, which is extremely fast. Heap allocations require more complex bookkeeping. Cache-friendly memory access. Stack memory is stored in a contiguous block, enhancing cache performance due to spatial locality. Automatic memory management. Oh, music to my ears. That's what we want. Automatic memory management. Amazing. So stack memory is managed automatically as functions are called and as they return. Inherent thread safety. So each thread has its own stack. Nice, nice. Heap allocations require synchronization mechanisms when used concurrently, potentially introducing overhead. So, one reason Go programs are efficient is that Go uses stack allocation for variables when possible, much like C. The Go compiler performs escape analysis to decide whether a variable can be allocated on the stack. On the other hand, languages like Python allocate most objects on the heap, which can impact performance. All right. So generally speaking, it's more performant to store a variable's data on video cassette. Could be. Is it ticker tape? Is it the stack or is it the heap? All right, let's go. So Stack Overflow. So the stack is great and all, but one of the downsides is that it has a limited size. So if you keep pushing frames onto the stack without popping them off, you'll eventually run out of memory and get a stack overflow. Yes, that's what the famous site is named after. So that's one of the reasons recursion without tail call optimization can be dangerous. Each recursive call pushes a new frame onto the stack, and if you have too many recursive calls, you'll run out of stack space. Okay, so assignment. Snakelaying is admittedly a fairly inefficient language. Don't tell the VC investors. Sometimes, rather than carefully managing memory, the snakelaying interpreter allocates a big chunk of stack data, simply because the creators, us, are too lazy to allocate the right amount. So anyway, the BDFL of snakelaying has allowed this laziness, but only to a maximum amount of 10 kibibyte. A single kibibyte is 1024 bytes. All right. So run the code in its current state. You should get a stack overflow, which will cause a segfault. Okay. So fix the pool size so that it allocates exactly 10 kibibyte. Okay, so if we run like this, then we're like, okay, so it says aborted segfault. All right, fine. And so we want to change the pool size. So we said 1024 times 1024 times 10. Interesting. But we only want the one 1024, right? Am I crazy? Because it says the maximum amount is 10 kibibyte. Okay, so let's get rid of one of the 1024s and try again. Okay, so I guess that's better. Size of pool 10 to 40. Okay, seems good to me. Let's submit. Oh, wait, let me check the potion. Let's activate potion, baby. All right, here we go. All right. Pointers to the stack. So we know that stack frames are always getting pushed and popped, and as a result, memory addresses on the stack are always changing and getting reused. Remember, the stack is only safe to use within the context of the current function. So let's get back to snakelaying's built-in 2D graphics library. Take a look at the new chord function. It accepts an x and y value, okay, x and y value, and creates a new pointer to a stack allocated chord t struct. Okay, fair enough, fair enough. Run the code in its current state. You should see something weird. Why don't the x and y values match the ones passed in on lines 16 through 18? Okay, so let's see. So we go 10, 20, 30, 40, 50, 60. All right, so let's see what we get. 50, 60, 50, 60, 50, 60. Oh, messed up, baby, messed up. All right, so when we did this, what happened? We did this, we declared this, we returned the address, so it overwrote it every time. That's messed up. Messed up, baby. So because we're accessing stack memory, the pointer created on line 12, outside of the function that created it, the memory has been deallocated and is no longer safe to use. Technically, the behavior is undefined, but it's likely that in this specific scenario, you're just seeing it get overwritten by the next function call. Thus, 50 and 60 always print. Okay, so fix the new chord function so that it returns a struct, not a pointer to a struct. Okay, so we'll just get rid of this. And then this will, so then we'll just dereference here, I guess, right? And then, does that mean we're okay? No, we need the address, excuse me, we don't need to dereference, we need the address so we can make a pointer. I'll try not to make that particular mistake so much. Okay, so cannot take the address of an R value for type chord T. Oh, interesting. What is that about? All right. Cannot take the address of an R value. Yeah, what's that about? Let's look here. Cannot take the address of an R value. The above expression gives you an R value, non-L value. Okay. So I guess we're just going to do this for now. Right? And then let's see if there's something else that it's going to tell us to do. So if we run now, does it say it's okay? So 10, 20, 30, 40, 50, 60. So returns a struct. This will force the compiler to copy the struct to the main function stack frame, and the memory will be safe to use. Okay, amazing. So let's submit that one, and let's see what it says next. I'm hoping it will tell us something about whether we could use pointers and stuff, because we are talking about pointers here, right? Uh-oh, we're going to the heap already. Okay. The heap. Memory management? Oh no. Okay, the heap. The heap, as opposed to the stack, is a pool of long-lived memory shared across the entire program. Stack memory is automatically allocated and deallocated as functions are called and returned, but heap memory is allocated and deallocated as needed, independent of the burdensome shackles of function calls. When you need to store data that outlives the function that created it, you'll send it to the heap. The heap is called dynamic memory because it's allocated and deallocated as needed. Take a look at new int array. Okay, so new int array int size. Oh, yay! So we're going to now malloc to the heap. So that's cool. That's cool, baby. So we totally do that, and then we return this pointer, right, to the new array, and now it's fine, right, because we put it onto the heap. Okay, fair enough. So let's see. So because the size of the array isn't known at compile time, we can't put it on the stack. Instead, we allocate memory on the heap using the standard lib's malloc function. Okay. It takes a number of bytes to allocate as an argument. So that's the size times size of int, and returns a pointer to the allocated memory, a void pointer that we cast to an int pointer. Oh, interesting. It seems a little bit, okay, so a void pointer that we cast to an int pointer. Okay, good to know. So the new inArray function's size argument is just an integer. It's pushed onto the stack. Okay. So this is just an integer. Assuming size is 6, when malloc is called, we're given enough memory to store 6 integers on the heap, and we're given the address of the start of that newly allocated memory. We store it in a new local variable called new r. Okay. And then let's see. So the address is stored on the stack, but the data it points to is in the heap. So let's look at some code that uses new int array. Okay. So we say new int array 6. We can say 69, 42, 420, 13, 37, 7, and 0. So the data is stored in the heap somewhere. So when we're done with the memory, we need to manually deallocate it using the standard libs free function. Okay, cool. So the free function returns, deallocates that memory for use elsewhere. It's important to note that the pointer still exists but shouldn't be used. It's a dangling pointer pointing to deallocated memory. Okay, so far so good, right? So run the get full greeting function in its current state. If you take a look at the main C file, you'll notice that it's testing to ensure that a pointer to stack memory is not returned, which you never should do because it's undefined behavior. Okay. Is on stack result is not false. So is on stack is to see if there is, so it takes a pointer. Okay. So let's see. So run the get full greeting function. So fix it so that it allocates memory on the heap and returns a pointer to that memory. Okay. Allocate memory on the heap. Okay, so this is not what we want. So we want to do it like in the example. So we'll say char pointer full greeting, right? We'll say equals, we'll cast to char pointer, we'll call the malloc, we'll pass in the size, we'll times size of char. So just like we saw there before. All right, so we won't do this. Then, so here, of course, we did check for a null. And what does it say here about checking for a null in the text? Did it say anything? Not really. So let's just run it like that real quick. So which test is skipped? Should truncate to fit buffer. I think we're okay. Let's try submitting. Nope. Should truncate to fit buffer. Never mind. String, let's see, string result is hey, should truncate to fit buffer. So the size, man. All right. So the truncate is going to be, shouldn't this be the size here? Is that what I left out? Honestly, that would kind of make sense. Let me just run it again since I already got a fail. Well, that was pretty obvious. um, dumb. All right, the Malloc function, memory allocation, is a standard library function in the C that allocates a specified number of bytes of memory on the heap and returns a pointer to the allocated memory. So this new memory is uninitialized, which means it contains whatever data was previously at that location. It is the programmer's responsibility to ensure that the allocated memory is properly initialized and eventually freed using free to avoid memory leaks. Okay, so if you want to make sure that the memory is properly initialized, you can use the calloc function, which allocates the specified number of bytes of memory on the heap and returns a pointer to the allocated memory. This memory is initialized to 0, meaning it contains all zeros. Okay. So we pass in a size t size for the number of bytes to allocate, and returns a pointer to the allocated memory, or null if the allocation fails. Okay, so memory for an array of 4 integers. Nice, nice. Handle memory allocation failure. Okay, cool. And free after it's been used. Okay, so this idea of manually calling malloc and free is what puts the manual in manually managing memory. So the programmer must remember to eventually free the allocated memory using free pointer to avoid memory leaks. Otherwise, that allocated memory is never returned to the operating system for use by other programs until the program exits, at which point the operating system will clean up after it, but that's not ideal. So, manually managing memory can be error-prone and tedious, but languages that automatically manage memory like Python, Java, and C# have their own trade-offs, usually in terms of performance. So, we're working on some of the dynamic memory management tooling that we'll eventually need to build a garbage collector for Snakeline. So we want to complete the allocate scalar list function here, all right? It should accept the size and multiplier parameters and should allocate an array of size integers on the heap, okay? So we will say, let's say int a array size, and then we'll say equals, and we'll say, I guess it's really more like int pointer to int a equals pointer to int malloc, and then we put in size times size of int. So then we say if a is null, return null. Okay. So then initialize each element in the list to the index times multiplier. All right, fair enough. So we'll say for I is less than size I plus plus, and then we'll say a sub I equals multiplier times I, right? And then return a. Okay, so let's try running. Assume that the calling code will eventually call free on the returned pointer. All right. Okay, cool. Let's go to the next. So the free function deallocates memory that was previously allocated by malloc, calloc, or realloc. Important. Free does not change the value stored in the memory, and it doesn't even change the address stored in the pointer. Instead, it simply informs the operating system that the memory can be used again. So, forgetting to call free leads to a memory leak. This means that the allocated memory remains occupied and cannot be reused, even though the program no longer needs it. Over time, if a program continues to allocate memory without freeing it, the program may run out of memory and crash. Memory leaks are one of the most common bugs in C programs, and they can be difficult to track down because the memory is still allocated and accessible even though it is no longer needed. All right. So we may be inefficient here at SnekLang, but we don't want outright memory leaks. So run the code in its current state. After a number of successful allocations, you should get a failure. The program is running out of memory due to a leak. Let's take a look. See how it's calling the allocate scalar? Okay, so we allocated like, it looks like 83 and then failed. Darn, that's messed up, baby. So yeah, so we're doing this in a loop, sure. We wanted 500 of them, but we only got to 83. Oh, that's terrible. Well, the lists aren't needed from loop to loop, so they should be freed. Okay, so we know we allocate here. All right, so that means we know that sometime before we start another loop iteration, we should free this, right? So if we do that, we should be able to allocate as many lists as we want because we return the memory in between iterations. Okay, let's take a look. So free list. And that's all you do, right? Let's take a look. Okay, so this time we got all 500, so that is better. Okay, let's submit. Okay, still got the potion going. Love it. Okay, so big Endian and little Endian. So while we are on the topic of memory, it's worth knowing about Endianness. Indeed it is worth knowing about. Endianness is the order in which bytes are stored in memory. The two most common formats are big Endian and little Endian. All right, so let's look at big Endian. In a big Endian system, the most significant byte is stored first, at the lowest memory address, okay? The most significant byte is just a fancy way of saying the biggest part of the number. All right, so let's say you have a hexadecimal number, 12, 34, 56, 78. Okay, so that means we'll start with 12 over here and go 34, 56, 78 in that order. Most to least. All right, so the big end is here. Okay, so the most significant byte is stored at the lowest memory address. All right, so if it's little Endian, then we go 12, 34, 56, 78 in reverse order, basically. All right, so the least significant byte, the smallest part of the number, is stored first at the lowest memory address. This is the format used by most modern computers. So using the same number, 12, 34, 56, 78, here's how it would be stored in little Endian format. 12, 34, 56, 78. The least significant byte is stored first. For the most part, you won't need to worry about Endianness when writing programs. The way data is read from memory automatically handles this, so we can spend our valuable time building e-commerce shops for the terminal instead. Good idea, good idea. Endianness becomes important in certain scenarios like networking. Yes, it does. Yes, it does. And working with binary files. So for now, just know that most modern systems use little Endian and the compiler takes care of how data is stored and accessed. So here we have little Endian. So A1 will have to be last, then B2, then C3, then D4. All right, let's go to the next. Pointers. Oh, wow. I feel like we're kind of moving along. I feel like I started off so slow. I'm still going pretty slow. But I think I've picked up a little bit. Anyway, so now we know what pointers are. So let's learn it over again. A pointer to pointer in C is just a pointer variable that holds the address of another pointer. Oh, incredible. So this allows you to create complex data structures like arrays of pointers and to modify pointers indirectly. The syntax is exactly what you would expect. A value, a pointer with 1 star, and a pointer with 2 stars. Is that exactly what I would expect? I don't know, but it's fine. It's cool. So, pointers to pointers, or pointers to pointers to pointers to pointers, you get the idea, are like a treasure map or a scavenger hunt. You start at one pointer and keep following the chain of addresses until you get to the final value. It's just a chain of dereferences. Okay. So if I start with some int quadruple star, like, oh, it has a memory address. Shall we see what's there? It says FF24. Okay, let's find, oh no, this is where I am. I'm at FF24. It says FF08, so let's go to FF08. Here it is. Oh, it's a triple int pointer. Well, that makes sense. It goes to FF14. Okay, FF14. Okay, what have we got here? It's an int double pointer. Okay, FF00. Let's find it. Okay, it's an int single pointer. FF1C. Okay, let's find FF1C. Sure. It's a 42. Oh my goodness gracious. So, complete the allocate int function. It accepts a pointer to an integer called pointer and a raw value. So, first, allocate memory for a single integer on the heap and save its address into a new pointer. Okay, so let's try that part first, I guess. So we'll say int pointer, I'm gonna call it, I don't know, I, because I don't really know what it's for exactly. I'll just call it I. We'll say it is int star Malloc, and then we're gonna say size of int. Okay, got it. So should we go ahead and check for null? Maybe we should. I'm just gonna put a comment. I'm not gonna do it if it's not asked for. So then update the memory address that pointer is pointing to be the address of the new pointer. Okay. So pointer equals address of I. Okay. Set the raw value of the integer that pointer now points to, well, that it points to through 2 address hops, to the value passed in. Okay. So we'll say pointer equals value. Is that it? Did we do it right? I don't know. If you take a look at test does not overwrite, you'll notice that while pointer does indeed unravel and point to the new value, the original value still exists at its spot in memory. We just don't point to it anymore. Okay, so let's see what happens. Should allocate pointer. Okay, so we didn't quite... Wait a minute. Should allocate pointer. So update the memory address that pointer is pointing to be the address of the new pointer. Okay, okay. So that was totally wrong. This should be this, and this should be... Ah, that's what it should be. Okay, cool. Well, that was a bit of a, I don't know. That was a bit of a brain blast. It was a bit of a confusing thing. A brain teaser. I don't know. Okay, let's go to the next. Array of pointers. So making an array of integers on the heap is pretty simple. So, for example, we can malloc some size of int times 3, and there we go. Bang. We can also make an array of pointers. It's quite common to do this in C, especially considering that strings are just pointers to chars. Okay, so that's a good example. So we have the char double pointer string array, size of char pointer times 3, and then we put these. Okay, cool. So SnekLang, being a super robust programming language toolchain, needs to represent tokens. These are strings of text that represent SnekLang syntax. Things like if, else, and def. They're represented as structs. You can see the struct in exercise H. Okay. So our token has some kind of string. It has a line and a column position. All right. Do I still have? Okay, good. So let's see. So the create token pointer array correctly allocates God, if I could even speak. It correctly allocates an array of token pointers on the heap. But notice that the addresses it's adding to each index are the addresses of the stack allocated inputs. Okay, let's take a look. So it says this part is correct. So we make this malloc count times size of token t pointer. Okay, so far so good. Now, as we go through and we increment the I, we're putting the address of a token. Okay, so we can't do that. So instead, we have to allocate new space for each token on the heap. Okay, so let's start with that. So we'll say token t star new token equals, and then we'll put token t star malloc, and then we'll put count, or no, we'll just put size of token, token t, and then we'll say if new token is null, exit 1, I guess. And then when we get to this point, we will say token t equals tokens sub I. Okay, so we'll make an assignment, and then we'll point this to, wait, this should be new token, excuse me. New token. And then this should just be new token. Okay, so allocate space for each new, allocate new space for each token on the heap, and store the address of the new space in the array. Copy the contents of the input struct into the newly allocated one. Okay, so let's try it like this, but then I want to make a change as well. So it says we skipped something, but I think it's okay. So that's, oh, another, man, they're really generous with these chests. They give out chests like crazy. Okay, so now let's try also, instead of doing this, let's say that we just go token pointers sub I. Is that right? And then this one also becomes token pointers sub I, all right? And then this one also becomes token pointers sub I. So we don't have the new token. Let's just see if it's the same. It should be, I believe. Okay, cool. Good, let's go to the next. Void pointers. So we've already discussed void, which essentially means nothing in C. So it's used in a few different contexts. So a void can be like part of this function signature where it returns nothing. It can be here where it takes no arguments. So because C likes reusing ideas, but with slightly different meanings, void has another use. So we already kind of mentioned the idea that malloc returns a void pointer. So let's just learn more about that, I guess. So a void star void pointer tells the compiler is that this pointer could point to anything. Oh, nice. So this is why void pointers are also known as a generic pointer. Since void pointers do not have a specific data type, they cannot be directly dereferenced or used in pointer arithmetic without casting them to another pointer type first. Okay. So casting to void pointers. So casting to and from void pointers in C is unique because void pointers are type agnostic. When casting a specific type pointer to a void pointer, no type information is retained, allowing the void pointer to point to any data type. However, you must cast a void pointer back to its original type before dereferencing it, as direct dereferencing is not possible. Okay, so this was listed as a void pointer, and then we were like, oh, can I get this number? No, this doesn't work because we don't even know what it is, right? It's a void pointer, but we can cast it back to int star, cast to appropriate type before dereferencing. All right, nice. So a common pattern is to store generic data in one variable and the type of that data in another variable. So this is useful when you need to pass data around without knowing its type at compile time. Okay, let's take a look then. So we have a enum for the data type. So we have int and float as a couple of options here. Nice. And then we want to print the value. We're going to take a pointer to something, and we're going to take one of these data types, which will be either int or float, and then I guess we could switch, but in this case just if, so that's fine. So type int, then we'll do this. Cool. And type float, we'll do this. Sure. So, I mean, sure, it seems fine. It seems kind of fine. It doesn't seem bad. So in snakelaying, we have to dynamically interpret snake code and store the values in memory. The snake object kind t enum defines the different types of objects that can be stored in memory. So let's complete the snake zeroOut function. It accepts a generic pointer to one of snake int t, snake float t, snake bool t. It should zero out the value field of the struct. Use the kind parameter to figure out which type of struct you are working with. Okay, cool. So we can have integer, float, or bool. All right. And there'll be a value either way. Okay. So let's go ahead and switch on kind, I guess. So we'll choose a case where it is integer. And in that case, we'll say so now we have to cast to snake int t, right? Okay. Like this. Pointer value equals 0. So we have to do this, right? Okay, and then break. Okay. All right, so the next case will be float, right? And then it'll be bool. And then this should be default. So in the case of default, I'm not sure what to do, if anything. But anyway, so in this case, this will be bool, right? Bool here and float here. All right, so then we'll put 0, 0 here, and we'll put false. I don't know, let's see. Unexpected type name snake int t, and that is on 6.8. Okay, so we tried to cast the pointer. Wait a minute, wait a minute. I put the star on the wrong side, which honestly how many times did I already do it correctly and then screwed it up that time for no reason? Well, maybe I won't screw it up so much next time. So let's see, run. So this should be 0, I think. Okay, so which tests did we skip here? Boolean should be zeroed out to 0. Okay. I'm gonna, before submitting this with a potion, I'm gonna take another quick step away and be right back. All right, that should be fine. Let's get back into it. All right, so let's see if this passes. I think it should. Oh no, let's hit the potion first. Yeah. Okay, so submit. Let's go to the next. Swapping integers. So snakelaying makes it easy to swap two values. So if I say cool person is Lane and uncool person is TJ, then we can go cool uncool equals uncool cool. Very nice. So before we do something more tricky, let's start with just swapping some integers. Complete the swap ints function. It accepts two pointers to integers and should swap the values of the integers they point to. You'll need to use a temporary variable to store one of the values while you swap them. Okay, so we'll say int c equals, and then we'll dereference the a, right? Then we'll say b equals, no, excuse me. A equals b, okay, and then we'll say b equals c, and then that's it. Let's do it. Let's do it. Okay. Let's go to the next. Okay, swap strings. Let's take it up a notch. Oh, really? Okay, a half notch, but still. Complete the swap strings function. It swaps the values stored in the string pointers. Okay, interesting. So remember, a char star star is a pointer to a char pointer, which means we can simply switch the address that we're referencing in our swap function. Okay. You won't need to use any string-specific functions for this swap implementation. Okay, so we're going to do basically exactly what we did before, right? So we'll say char star c equals, and then we'll dereference a, Sure. And now A equals B. And now B equals C. And that's, I mean, it's just what we did before. Nice to reiterate. A half notch. Cool. Okay, let's go hit up the next. Generic swap. So for the previous swap implementations, we've known the type of the data we want to swap. Because we knew the type, the compiler knew the sizes of the data we want to swap. Okay, sure. However, to make a generic swap, we will need to provide the C compiler with the size of the data that we are swapping, because void star loses that type of info, that type info. Okay, so our new interface for swap will include the size. So void pointer 1, void pointer 2. So we're going to learn something new here, right? So the other problem we're going to have is that directly assigning pointer values does not work the same way with void star. So instead of using pointer 1 equals pointer 2, we will use memcopy. Memcopy. So it's included in the string h library. Cool. So we just need a destination, a source, and a size. And these can be void pointers. Very fun. All right, so to move the data from pointer 2 to pointer 1, we'll just go memcopy pointer 1, pointer 2, size. Amazing. Okay, so allocate memory for a temporary buffer to store the data using Malloc. Okay, there we go. So we'll say void star vp3 equals Malloc size. So far, so good. If vp3 equals null, then we will return. Okay. Memcopy. Use memcopy. So we have to make 3 copies again, right? Is that right? Yeah. Okay, so we'll go memcopy, and the destination will be vp3. The source will be vp1. All right. And then this time we'll do vp1, all right, to vp2, sure. Or no, excuse me, we'll do vp2 to vp1. And then the source will be vp2, and this will come from vp3. Okay, don't forget to free. Okay, too few arguments. Oh. Okay, so once we're done, we'll free VP. Good reminder. Okay. All right, so I guess that's fine. We still have plenty of time on this potion. Cool, cool. Let's go to the next. Low-level stack. So if you've taken our data structures course, you've already implemented a stack. We're going to implement a stack again, but this time we're going to do it while This time we're going to do it while manually managing the memory of generic pointers. So we'll get to have our first deeper exploration of generics in C. Remember, that just means void star. As well as creating a data structure we will later use in our mark and sweep garbage collector. Okay, cool. So let's take a look at snakestack H, specifically the stack struct. Okay, so it has a count, a capacity, it has data, which is a void star star, and that's it. All right, cool, cool. Pointer to all the generic data. So count number of elements in the stack, number of elements the stack can hold before it needs to be resized in memory. Okay, so it looks like we're gonna do, yeah, we're gonna do a bunch of these. Okay, so we're just gonna start with the basic, the new stack function. Okay. So we have to return a pointer to a stack. Let's take a look. So allocate memory for a new stack struct on the heap. Okay, so I'm gonna say stack t star new stack equals, then we'll do stack here star Malloc. Okay, sure. And then we'll do capacity here. That doesn't seem right. It should just be size of stack t, right? Yeah, it should just be size of stack t. Okay, and then so if new stack is null, return null. Okay, sure. Initialize the count to 0. Okay, so we'll say new stack count equals 0. Sure. New stack capacity equals capacity. Okay. Data. Okay. So we'll say new stack data equals. Okay, so for this, we have to cast to void star star, right? Because that's what it is. So then we malloc size of void pointer times capacity, right? Okay. If new stack data is null, return null. Sure. And then return new stack. Okay, let's see what we get. So expected identifier. Well, nice reminder, nice reminder. Okay, so that's cool. I think we're good here, probably. It seems like a simple one. It's only difficulty 6. Okay, next. Stack push. Okay, so let's actually store some data instead of just allocating memory for no practical purpose, also known as Haskell programming. Oh no. Hey, you know what? Why can't we all just get along? So as you know, our stack has a count and a capacity, but what happens when the count is equal to the capacity? Ooh, we need to make room for more data. So we'll take a simple approach. Whenever we run out of capacity, we'll double it. That way, we don't have to reallocate memory on every push. So for example, so we start with 0 and 4, all right, so there's nothing here. Then we add 1, we add 2, we add 3, we add 4, and then we're going to have to discover that we've run out because now we're going to increase the capacity to 8. All right. So complete the stack push function. It safely adds a new object to the top of the stack. So remember, the size of the data array is the capacity of the stack, and the number of elements that are actually in the stack is the count, which is less than or equal to the capacity. Okay, and look, they break it all down very nicely for us. So here we go. Looks like a pretty simple one. So we're going to start by saying, you know, if stack count is equal to stack capacity, so then we are going to reallocate, and then do we copy everything over? Wait a minute. So we're going to use realloc. So does realloc mean we don't have to copy it? Used to resize memory. So it'll take care of copying for us. Okay, wait. Used to resize memory that was previously allocated with malloc or calloc. Interesting. Well, that's neat. I didn't know that at all, I don't think. Actually, I do think I saw a mention of that somewhere and it just didn't stick. Okay, so let's say we're going to double the stack's capacity. Okay. We'll just delete that. So we're going to say stack capacity, okay, times equals 2. Sure, so we did that, doubled. Reallocate enough memory. So we're going to say stack data equals, and then we're going to cast void star star. We're going to call realloc, and it says we pass in a pointer, so that'll be stack data, and then the size will be stack capacity times size of void pointer, right? So then if let's see, if realloc fails, free the old data and return immediately. So if stack data is null, talk about slow typing, I don't know, then we will free stack data return. Okay. If it succeeds, update the stack's data field to point to the new memory. Okay. So we can't do this because that will destroy the stack data that we had before. So this is going to be so stack data, this is going to be new, oh gosh. Okay, so if it was null, then we, wait, do we have to, oh no, we free the old data? That doesn't, wait a minute. So we tried to realloc, free the old data and return immediately. What does it tell us about the realloc again? So small boy, Malloc, large boy, realloc, and I think I've missed something important here. Reallocates the given area of memory. It must be previously allocated by malloc, calloc, or realloc and not yet freed with a call to free or realloc. Otherwise, the results are undefined. Shoot. So if there's not enough memory, the old memory block is not freed and null pointer is returned. I think I've misunderstood something. It seems like, so if it fails, free the old data? That doesn't quite seem right. It's all right. We'll try a couple different ways. Yeah, because we don't free the null pointer. Free the old data and return immediately. Yeah, that seems crazy. But sure, we'll do what it says, I guess. I have my doubts. In this case, we will say I have my doubts. So in this case, we will say stack data equals new stack data, right? Okay. Yeah, this, I have my doubts. So add the new object to the top of the stack. Okay, so we're going to say stack data sub stack count equals obj stack count plus plus. So we'll try that. Oh gosh. Use of undeclared identifier. I guess it accepted it. Let's see if it also accepts it if we don't do that. Okay, accepted either way. Yeah, free, because specifically, like, so if if there's not enough memory, the old memory block is not freed and null pointer is returned. So that, I mean, that seems like the way it should be, I would think. Anyway, let's go ahead and go to the next. Stack pop. As you should know by now, items go on and off the stack from the same end, last in, first out. Don't worry, the pop method is much simpler than the push method in our case because we don't have to worry about resizing the stack. Amazing, love it. So let's take a look. If the stack is empty, return null. So if stack count is 0, return null. Stack count minus minus. Honestly, this is the kind of thing I just tend to do it in one line. Okay, let's see what we got. Okay, I'm chill with that. Let's go to the next. Stack free. So in C, we don't have a lot of abstractions at our disposal. There's no classes, destructors, functors, monads, made-up category theory words, etc. Okay, we've got data and we've got functions just the way Dennis Ritchie intended. Very nice. So to make it easier to work with our stack, we're going to build our own little free function that will clean up all the memory that we've allocated for our stack. Okay, stack free. So if stack is null, return, sure. If stack data is null, return. I'm not sure I quite jive with that. I feel like even if the stack data is null, shouldn't we free the stack itself? Apparently not. I don't know, but you can assume all of the elements inside of the stack are already freed. That's not our problem. Oh, I feel like it's about to be our problem pretty soon. Anyway, so free the stack data. So we'll free stack data, sure, and then free stack, and that's it, baby. Maybe I'm crazy here, maybe I've misunderstood something, but I feel like it would make more sense to me if it were more like, if it's not null, then free it, and then free the stack. Do you think it'll accept that? So it accepts it either way. All right, well, we'll see. Dangerous push. Up until now, even though we made our stack with void pointer, you'll notice that we've only stored plain old int pointers. I want to show you that you can actually store anything in the stack, even heterogeneous lists. Oh, that being said, this is usually a bad idea. So TJ likes to use words like heterogeneous to keep kids who don't read good at bay. He meant to say you can actually store anything in the stack, even lists of different types of data. Okay, cool. So now we're going to do something pretty gross to demonstrate the wise words of one of the philosophers of our time. With great power comes great responsibility, says Uncle Ben. So I'm going to have you push an int star and a regular old int directly onto the stack. A bad idea. I just want to show you that you can store anything in a void pointer, even values that aren't pointers at all. Oh no! Alright, so complete the scary double push function. Alright. Okay, so we get a stack S. We're going to say S dot, we're going to say stack push, and we're going to pass in S and a void star 1337, I guess. If we must. And then we're going to say int star new int equals Malloc, or excuse me, equals int star Malloc size of int. Okay. And then we're going to say, honestly, let's just put the quick check here. If new int is null, return. It didn't say to. It didn't say specifically to do it here. So set the value. Okay, so we're gonna say star new int equals 1024, sure. And then we're gonna say stack push s void star new int. Let's see, do we have an error in here? Well, it says one is successful, I guess. So that's neat, that's neat. Okay, let's go to the next. Multiple types. So we saw that we can push both int and int star types into the same stack. Again, a bad idea. In this example, we'll see that not only can you push values and pointers into the same stack, but you can also push different types of values into the same stack. This is, once again, a terrible idea, but the thrust of what we're getting at here is C doesn't care what you put in memory. It's bytes all the way down. Nice, love it. So fortunately, C doesn't let you do these conversions automatically, but it still lets you do them. When you're working with void star, you're working with raw memory addresses, and you can cast them to whatever you want. All right, here we go. So stack push multiple types. So we're going to allocate. So we're going to say float star new float equals float star malloc size of float. Oh, this one's a 9 apparently. That's crazy. Then we'll say char star new string equals char star malloc let's see. Snakelang is blazingly slow. So when we allocate this one, don't we need the string length? It looks like we included the string, so let's say char star message equals snakelang is blazingly slow. Oh. Well, I guess it's true. And then we'll say int message length equals string length message. And we'll see if that's right. And then we're going to say size of char times message length, I think. Malloc size of char times message length. And then we're going to stack push both of these. So here we're going to say star new float equals 3.14 stack push s void star new float. Okay, and here we're gonna say new string equals message, yes, and then we're gonna say stack push s void star string. I don't know. We'll see. Nope. Segmentation fault. Oh, goodness. So this one is a difficulty 9 indeed. All right, so where did we F up here? So, once again, still lets you do them. Okay. Let's see. If I look back... Uh-oh. So if I look back here, we did stack push s void. Okay, I think that part is maybe fine. So the new int is, in that case, is a pointer. Oh, wait a minute. Let's do printf Did I get something printf? Undeclared library function. Oh, it's standard IO. I don't have it yet. Okay, so I got 27. I think that's probably right. Aborted segmentation fault. Let's see. So we're not supposed to free these. They're getting pushed into the stack. Okay, let's see. Allocate. Okay, it printed that. Snakeling is blazingly slow. But then we're supposed to push void star new string. When we do the stack push, it's like this, void star object. And wait, can we edit these? Is this the same thing I put in, or is this different? This is different. This is different from what I put in. Okay, let's see. So segmentation fault when we tried to stack push, I guess. or not. I don't know. Aborted segmentation fault, but after saying hi. Okay, so what did we try to do here? Multiple types stack, okay. I'm not too sure. Let me see. So we tried, so it's just the one test. Run, multiple types stack. I must have messed up something pretty obvious. Yep, I did. Oh no, that's not it. Huh. So 28, SnekObjects is blazingly slow. We could print high here. Stack push multiple types. Stack push S. Oh man, I don't know why I'm getting aborted. I don't know why. Okay, push the char star onto the stack using stack push. What did we do in the previous one? So we malloc size of int here. Allocate a float on the heap and set the value that's pointed to 3.14. Okay, so let's say that we are going to not do any of the rest of this. Let's just try the first part. Okay, cool. So 0 of 1 test successful. All right, so it didn't mess us up in that first part. I'm guessing that it won't mess us up as long as we don't do this extra stack push, right? Okay, yeah, so should have 2 items in the stack. So we didn't do the second stack push. It's supposed to be a SnekObjects is blazingly slow. Oh, no. We have to do string copy. What the hell am I doing? That's crazy. String copy. That was pretty obvious. Did you mean string copy? Yeah, I guess that's probably it. Interesting. Very interesting. Let's go to the next. SnekObjects. Objects in C? No way. However, SnekObjects is built in C, and everything in SnekObjects is an object, a quote-unquote object. So to be clear, not a class or object-oriented programming object, but a higher-level data structure that holds some metadata about itself. For example, it will store what type of data it holds, which could be int, float, string, etc., the size of the data it holds, the data itself, and how many references to itself exist, at least later when we build our own garbage collector. Ooh, very exciting. This is actually good progress. This is the third to last, this is the third to last chapter here. Dang, nice. Nice, nice, nice. I'm getting excited. Oh, I'm out of potion time, too. I'm gonna crack this open. Okay, so this last point is critical. Because snakelang is a garbage collected language, we need to know how many references to an object exist so we can free it when it's no longer needed. Okay, so we are going to complete the missing definitions in SnekObject-H. So here's a breakdown of all that this file should define. Okay, so we're going to have a... Shouldn't we have a Pragma once or whatever it was called? Yeah, Pragma once. Okay, so we should have a Typedef, and that is going to be enum SnekObject kind. We're just going to start with integer, apparently. So that's fine. And it's going to be SnekObject kind, T. Okay, cool. So then we'll have a union SnekObject data. So we kind of have already seen this stuff, I guess, right? So to start with, we're just going to have the vint, which is int SnekObject data t. Okay, a struct SnekObject. Okay, so typedef struct SnekObject, which will have SnekObject kind and SnekObject data. Did I miss anything here? I think it's okay. Let's keep going. Oh, I need another potion. Here we go. Oh, incidentally, I hit level 148. And I think that that is one of the highest levels. The only other guy, this guy, he's at 147 still. So I believe, I'm not going to check it at a more detailed level right now, but he's still 147. I believe this means that I am the first. Oh, in fact, it does. Look, he's leaderboard rank 2, and he's 147. Okay. If I go to my own self, I'm leaderboard rank 1. So I'm the first to reach level 148. Very nice, very nice. Anyway, let's go back. Okay, so we just did this, right? Okay, let's go to the next. Integer. So let's start simple with a single integer object. So the difference between a snake integer and a regular C integer is that the snake integer is allocated on the heap and can store additional metadata about itself, which for now is just its type. So let's see the meme. So the virgin C integer is allocated on the stack, doesn't know when it's being used. Ah, man, we can do better than that. We can create the Chad snakelang integer. Is allocated on the heap, knows when it's being used and abused. Well, we'll see, we'll see. All right, so complete the new snake integer function in the SnekObject-C. Okay, so this should use Malloc to allocate heap memory. Do we already have this defined here? New snake integer, sure. Okay. So we need a snake object t. So we'll say snake object t new object equals snake object t star malloc size of snake object t. A little boilerplatey, isn't it? A little boilerplatey. Okay, so then if new object is null, return null. Sure. So set the kind field. So new object kind equals integer. All right. New object data vint equals value. Yeah. Return new object. I think I may have messed something up in here. Let's see. I might be okay. Yeah, that says it's okay. So let's move on. Let's move on. Okay, float. So needs floats, obviously. So now we need to add a float option in here. Okay, let's look it over. So needs floats, obviously. How else will all the crypto bros write weird floating point bugs into their smart contracts? That is necessary. So how do we store both floats and ints into the same type? So we're going to use the union and enum features in C to be able to do this, just like we discussed in previous chapters. So you will need to extend the existing snake object kind t and snake object data t types to be able to include both int and float. So right now we just have int, and we will continue to add more types in the following chapters to exercise your newfound mastery of memory, your mastery of memory management. For some reason, it makes me think of Master of Magic. Okay, so you will need to edit 2 files in this lesson. Okay, so we're good here. Just add float. Float, okay. And here, simple, we'll just have a float option. Sure. Declare the new snake float function. Whoops. So this will be called float, and it'll take float instead. So then we will go over here, allocate memory. Okay, so here it is. So we'll allocate memory for a new pointer to a snake object t. Okay, let's start with that. So snake object t pointer new object equals snake object t pointer malloc size of snake object t. That's a boilerplatey line. Every time I see it, I'm like, So if new object is null, return null. Null, there we go. So then new object kind equals float, right? Float. New object data v float equals value. Return new object. Simple as that, baby, right? Right? I think so. I think that's about it. Okay, let's go to the next. String. So now we're going to do our first object that has something additional allocated. Okay, interesting. So when we allocate memory for a snake object, that reserves memory for the object itself. Okay. Small data types like integers and floats are stored directly in the object, so there's no need for additional memory allocation. Strings, however, are a different story. Strings in C are just arrays of characters, and because they can be any length, we need to dynamically allocate memory for the string data separately from the object itself. Okay, so here's a hello world string, and so of course we know that there are all these different chars in there and the null terminator. Okay, so in SnekObject H, we are going to add float as another option here, or excuse me, we have float. I said float because I was clicking on float, so we're going to add string as another option here. We're going to add char star v string here. Char star v string, okay, cool. And then this will be string, sure. And then this again will be char star. All right. Cool. And then in here, we've already got this. It takes a char star value, which is what we have here. Okay. So we're going to allocate a new, okay, so let's just copy this. So SnekObject T obj Malloc size of SnekObject T. Okay. Fair enough. And then if object equals null, return null. Fair enough, fair enough. Calculate the length. Okay. So I'm just going to put int len equals string length value. Okay. And then we're going to put char star new string equals malloc size of char times len plus 1. Okay. If the allocation fails, return null and free the memory allocated for the SnekObject. Okay. So if new string is null, free obj, return null. Copy the data from the input value into the new string field you just allocated using string copy. Okay, so we'll say string copy, and we'll pass in our destination, which is new string, and our source, which is value. And then we'll say obj.kind, or it should be arrow kind, equals string, and then obj data v string equals new string. Return obj. Let's see what it says for us. Seems okay to me. All right, how are we doing here? Pretty good. Vector 3 is going to be the first SnekObject that can hold a reference to another SnekObject. It's a collection type, a type that holds other types. Arrays, lists, dictionaries, and sets are all examples of collection types. We won't implement all of those types in this course, but they each will follow the same pattern that we're establishing here with vector 3. So vector 3 is similar to a Python tuple that contains exactly 3 SnekObject elements. Hey, we've got to start somewhere, I guess. All right, so in the SnekObject H, forward declare the SnekObject T. So let's create that. So we'll say typedef struct SnekObject T. Okay. Create a new struct called SnekVectorT. Okay. That has 3 fields. Okay. We're gonna, yeah, wait a minute. Create a new struct called SnekVectorT that has 3 fields. Okay, well, let's see how this works. Okay, so I'll go Typedef struct SnekVector3. SnekObject T star X, right? Y, Z, okay. SnekVector T, all right, sure. Add a new enum value. Okay, so vector3 is going to be an option here. And then SnekVectorT field to the data. Okay. So this one will be SnekVectorT. Is it a pointer to it? It is, right? Or is it? No, it's not. It's probably a value. Okay. Declare the new SnekVector3 function. So when we, wait a minute. So in the function signature, what do we pass in? Do we already have that here? I think it's just 3 SnekObjects probably. Yeah, okay, cool. So it's going to be SnekObject T, right? SnekObject T, X, Y, and Z. Okay, so is that what we ended up with here? X, Y, and Z. Okay. Note that the vvector3 field is not a pointer to a vector3. It's directly allocated. Okay. That's good. Directly allocated inside the struct. We can do this because we know the size of the vector. It's only 3 pointers wide in advance. Okay. So in SnekObject C, complete the new SnekVector3 function. And that is going to be, if any of the inputs are null, return null. Okay, okay, fair enough, fair enough. So if x is null, or y is null, or z is null, return null. Messed up, messed up. Okay, so allocate. Okay, I'm going to copy that again. Okay, Malloc. Yep, okay. Set the kind, let's see, set the kind fields to the appropriate enum. So obj kind equals vector3. Okay. Create a new SnekVectorT struct and set the x, y, and z fields to be input pointers. All right. So then we'll say, oh, but do we have to allocate? No, we don't. We just have to go object data. I guess we do have to kind of do this. I'm not totally sure. Let's see. So if we go dot v vector3 and then say equals and then just literally put x, y, z, Shouldn't that be okay? Yeah, I'm not sure. I'm not sure. Snake vector t. Where is that? I have it here. Is it in the wrong place? Okay. Expected expression. So I don't think we can do it like that. What if we do snake vector t? No, I don't think so. I think we just have to do something like snake vector t u vector equals x, y, z. Yeah, it's a little funny that we have to do it that way, but I guess it's fine. Oh my gosh, they're so generous with these chests. They give you these chests like crazy. Okay, cool. All right, let's go to the next. Array. Let's add a dynamically sized array to snakeling. We'll do it in two parts. First, we'll just create an empty array. In a later lesson, we'll make it useful. Very nice. So, add a new enum value to the snake object kind t enum called array. Okay, dynamically sized array. This is going to be great. Okay, so add an array there. Create a new struct called SnekObjects. So that is going to go by the vector. Where's the vector? This one? Okay. So we're going to go type. Wait. Yeah, so Typedef struct, and it has a size t size, and it has a snake object t double star elements. Okay, sure. And then it has the name snake array t. Fine. Okay, then the v array is going to go in here. So that's snake array t v array. And then we'll declare this new function. So it's going to be called, let's see, SnekObject t pointer new snake array. Sure. And what do we need to pass in here? Do we need to pass in the size and like an array? Let's see what it looks like. Looks like just a size. Okay. Looks like just a size. So size t size. Yeah? Okay, so it should accept a size as an input. Okay, I'm seeing that. I'm seeing that, baby. So allocate memory for a new pointer. Okay, so let's copy that again. So allocate memory for a new pointer. If the allocation fails, return null. Allocate memory for a new pointer to an array of SnekObjects. How much memory should you allocate? Just enough for the size of an array pointer, right? The size of a pointer for each element in the array. Yep, I should have thought about that a bit longer. All right, so anyway, so SnekObject. Why does that say DT? What the heck? DT? So that DT must just be wrong, right? I think I just put that in there without realizing it. Okay, so SnekObject T, pointer, new array equals Malloc, size of SnekObject pointer times size. Okay, and then we're going to say if new array is null, we will free obj and return. Okay. Then what's next? So use calloc instead of malloc so there is no junk in our array to start. All right, sounds good. Okay, and then set the kind field. All right. Array is what we put, right? Okay. And then we're going to say wait a minute. So we're going to say snake array T new data equals Malloc size of snake array T. And if new data is null, free new array, free obj, return null. Okay, and then we'll say new data size equals size, new data elements equals new array, obj data dot v array equals, oh my gosh, array equals new data, return obj. Okay, kind of ended up a little boilerplatey. I guess we didn't get it right. So use of undeclared, oh, SnekObject. This was supposed to be SnekObject T. And here's, okay, so this V array Wait a minute. Okay, hold on. Create a, oh my gosh. Yeah, I messed that up completely. It was supposed to be SnekArray T new data equals, and then it was just literally supposed to be size new array. We weren't supposed to do any of that. Okay. All right, let's move on to the next. Going pretty well so far. I thought I was starting off so slow, but I'm pretty happy with the rate that I'm going through this now, I think. We can make empty arrays, which is pretty useless, but at least the bones are there. So let's make them useful by allowing us to store and retrieve values from the array. So SnekArray set sets a value at a specific index in the array, and SnekArray get gets a value at a specific index in the array. Okay. So we're just going to fill these in right here, I guess, right? Okay, so if SnekObj equals null or value equals null, return false. Can I do false, I think, or does it have to be like 0? I wasn't super clear on that. Let me just see. C false. Okay, yeah, let's just say 0. Okay. So if the object's kind is not array, return false. If kind is not array, okay. If the index is out of bounds, return false. Remember, the varray field has a size field. Okay, so if index is, so it's a size t. So you just say if it's greater than SnekObj data.v array size, set the value in the elements array at the specified index to the new value. So we'll go SnekObj data v array elements subindex equals value, right? Okay, so then when we come to this one, we're going to say if SnekObj is null, return null, sure. If SnekObj kind not equal array, return null. If index greater than SnekObj data v array size, return null. Return SnekObj data v array elements index. Okay, where are we at? All right. Step aside. I'm going to step out for 2 more minutes here and come right back again. All right. Well, kind of a longish break. Okay. Let's go at this and finish up. All right. So let me hit this. Feels like this is getting a little repetitious, but whatever. Let's keep going. Okay, length. So now that we have all sorts of snake objects, integers, floats, strings, arrays, etc., we need a convenient way to get the length of any snake object. In Python, snakelang's dreaded competitor, it's as easy as print len x. Okay, so as a Python dev, you don't have to know the value of x ahead of time, because Python keeps track of it under the hood for you. We want the same capability in snakelang. All right, so the snake length. Okay, here we go. So if obj is null, return -1. Okay. If obj kind is integer, or obj kind is float, return 1. Okay, cool. All right. If Object kind is string. Then we will return string lang. And we have that imported, it looks like. So we'll just go object data v string. Okay. If object kind is vector 3, return 3, sure. If object kind equals array, return dot kind, my gosh. Return object data dot v array size return -1. Okay. Oh, missed something. Okay. Objects. Okay, let's go to the next. Add. So, Python objects can have an add method. So this is the final lesson on objects, and it's a big one. Oh, really? Difficulty 9, huh? Take your time. You'll be using a lot of the functions that you wrote in past chapters to complete this one. Okay. Complete the snake add function. All right, so if A is null or B is null, return null. Sure. If A kind is kind again, I don't know what I'm doing, is integer, if B kind equals integer, then we are going to return new snake integer A data dot v int plus B data v int. Okay. If B kind is float, return new snake float. Okay. So this time let's cast to float A data v int. Okay. Plus B data v float. Okay. Return null. Then we're going to say if A kind is float, if B kind is integer, return new snake float, and again float. But this time we'll put B data v int plus A data v float. If B kind is float, return new snake float A data v float plus B data float. Okay. Return null. Sure. Okay. If A kind is string, if B kind is not string, return null. Calculate the length of the two strings and create a new string with the combined length. So we'll say int lang equals. I'm pretty sure that should actually be a size, probably. Lang equals string lang a data b string plus string lang b data v string, and we'll plus 1 for the null terminator, I guess. So then we'll say char star new string equals, and it says calloc, so we'll calloc, and we'll put len times size of char size of char, okay, and then use string cat to append the data from A and then B to the temporary string. Okay, so string cat new string A data B string, string cat new string B data B string, and is that it? No. We're going to return, oh no, we have to free first. So we're going to say new snake string returns a we're going to say SnekObject equals new snake string, new string, then we will free new string, love it, return new object. Okay, next we're going to say if A kind is vector 3, if B kind is not vector 3, return null. Let's see, recursively call snake add for each of the X, Y, and Z fields. Fair enough, fair enough. So yeah, I love it. I love it. I love it, I love it, I love it. Okay, so we are going to return new snake vector 3, and this is going to be snake add, that's the name of this. Snake add. So we're going to pass in A data what is it? V vector 3 dot x. This is going to look a little crazy, but okay. So that's what we're going to be returning. And then this is going to be b data v vector 3 dot x. Okay. This here's got to be a dot, I think. Okay. And then here, this will be a y and a z. Yeah? Okay, cool. Okay, next. If a kind is array, if b kind is not array, this really isn't too bad at all. It's kind of boilerplatey more than anything, I think. Is not array, then return. I don't know. I mean, they're giving us such detailed instructions. It is nice in its way. I think it's nice. So anyway, so then we're gonna say SnekObject star new array equals new SnekArray, and we pass in a data v array size plus b data v array size. Okay. So then we'll say for int I equals 0, I less than a data v array size I plus plus. And then we do array, what is it? SnekArray set. And we pass in the new array. And there are so many places there could be mistakes here. It's kind of a lot. A data v array. Or actually, do we do get? Yeah, we do get. SnekArray get a I and then the I itself, I think, goes here. Let's look at the SnekArray set again. SnekArray set. Yeah, the index is there. Okay. So then we're gonna go for int I equals 0, I less than b, v array size, I plus plus. We're gonna go SnekArray set, new array, I plus a data v array size, SnekArray get vi. Okay. Return new array. And then at the end we return. Okay, so expected expression on 37. Return new snake vector and I put in 3 things, and it says, wait a minute, that matches there. New snake, wait. Oh, is this trailing comma not allowed? It might not be, let's see. Okay. All right, well, that's not bad. Just one spurious trailing comma in all that. That's not too bad. But again, I was following these detailed directions. But, you know, it was a difficulty 9, too. Just one spurious trailing comma in a difficulty 9. I'm going to give myself a pat on the back. I don't care. All right, let's go to the next. Chapter 10, Refcounting GC. As you're painfully aware, we've been manually managing memory throughout this course with our C code. You know, it's funny to call it painfully, but it hasn't been painful. It's been fun. It's been fine. It's been neat. So, let's see. So SnekLang, the language we're building, has automatic memory management. Specifically, it makes use of a garbage collector. Cool. So in C and C++, management of heap memory is done manually with Malloc and free. New and delete in C++. Rust has a compile time system that ensures memory safety. Zig gives the programmer access to allocators to manage memory. Yay! So these are all examples of manual memory management. The programmer has to write code that keeps track of and frees memory. So what's a garbage collector? A garbage collector is a program, or part of a program, that automatically frees memory that is no longer in use. So languages like Python, Java, JavaScript, OCaml, and even Go use garbage collectors as the code is running. To manage memory. It's automatic memory management. Automatic memory management can be a huge productivity boost for developers. Less code and sometimes fewer memory-related bugs. But it typically comes with a performance cost because, like Forrest Gump, the garbage collector is always running. Now we know. So it's no coincidence that C, C++, Rust, and Zig are all great choices when you need to squeeze every last drop of performance out of your code. Okay, so which of these? Go is the option with automatic memory management amongst these. So let's go to the next. Refcounting. So one of the simplest ways to implement a garbage collector is to use a reference counting algorithm. It goes something like this. So all objects keep track of a reference count integer, all right? When that object is referenced, its reference count is incremented. When any object that references an object is garbage collected, the reference count is decremented. When any object's reference count reaches 0, the object is garbage collected. Okay, well now we know. So in SnekObject H, add a refcount field to SnekObject T. So let's take a look here. So it says it can be just an int. All right, SnekObject T. There we go. So let's add that in here. Refcount, right? And so we're going to complete the new SnekObject function. Let's take a look. Okay, so in this one, we allocate a SnekObject T on the heap. Be sure to initialize the memory to null. All right, so we'll start with that. So we'll say SnekObject T star new object equals calloc, right? And we'll say size of SnekObject, size of SnekObject. And then we're going to go, so if new obj is null, return. Okay. New obj refcount equals 1 and return the pointer to the new object. Return new object. Is that it? Okay, well, it's bit by bit, baby, bit by bit. Increment. Okay, so we need to be able to increment the reference count of a snake object. Okay. So we're gonna say if obj equals null, return, I guess. So it says if the object is null, it should do nothing but safely. What do you think that is? This is an easy one, right? It's only difficulty 4. It should do nothing but safely. Okay. So then obj ref count. That's it, right? Not too shabby, not too shabby. Okay, next. It's still glowing. All right, decrement and free. So now things are going to get a touch more complicated. In a ref counting GC, the interesting stuff happens when the ref count equals 0. That's when the garbage gets collected. So when the ref count reaches 0, there are no references to this object anymore. So we need to free the memory automatically. That's the whole point of a garbage collector. So for our first pass at this, we'll only handle integers, floats, and strings to keep things simple. As we go a little further, we'll implement it for the rest of the snake object types. Nice. Okay, so if obj is null, return. Sure. Obj ref count minus minus. If obj ref count is now 0, then we ref count free obj. Okay. Now we need to do the ref count free. I didn't need to compile that. Okay. So ref count free. So we're gonna say if obj kind is integer or obj kind is float, then we are going to free obj. If object.kind is string, free obj data v string, free, this really should be else, free obj. Okay, is that it? If it's any other type, do nothing for now. Okay, let's give it a shot. Looks good to me, baby. Vectors. Okay, so we've arrived at our first container type. What makes vector 3 not like the other types is that it holds other snake objects. That is, it references them. So they are contained in its x, y, and z fields. When we create a vector and place objects in those fields, we need to increment the ref count of each of those objects. Otherwise, we might accidentally free its contents and be left with vector holding garbage memory. Yeah, we don't want that. Okay, so we're going to update the new snake vector 3 function. It should ref count inc each of its 3 objects. Okay, cool. So are we in the right place? Right here, right? So we do this, and so we need to ref count inc on the object that comes in. So in this case we don't, and in this case we don't, but in this case we need to do it. So let's add it in here. So we're going to say ref count inc x, ref count inc y, ref count inc z. I guess that's it. Yeah, I think that's right. So then, are they, well, these aren't copies, are they? Yeah, these should be the originals. Okay. So when we ref count free, we are going to put in a vector case. This is quite different from what I did a minute ago, and honestly much, much better. Okay, so this is where we're doing it, right? Okay. So we're going to call ref count dec, right? Which is down here somewhere. Okay. So that's going to be object data v vector 3 x, right? Okay. Sure. And then we need to, once we've done that, well, I guess that's it. Okay, cool. Next, arrays. Okay, so ref counting for an array is similar to the vector 3 kind. However, since an array has a dynamic size, which will add some additional complexity. So the assignment is update the SnekArray set function. Okay, here it is. Increment the ref count of the object that is being set into the array. Okay, so if we set it into the array, that's here. So let's go ahead and do that then. So we're going to say ref count inc value. Okay. If there was already an object at that index, decrement its ref count. Okay, very important. I wasn't even thinking about that at all. Ref count dec SnekObjects data v array elements index. Okay. Ref count free. So if it's an array, then we need to iterate over each element. So we need to add case array, right? Case array. So iterate over each element. Oh, this kind of looks nicer than what I did before, I think. But anyway, so I'm going to go for int I equals 0, I is less than, and we're going to put obj data v array size I++, and then we're going to say ref count dec obj data v array elements sub I. So then when we're done with that, we free obj data v array elements. Okay, and that's it. So break. Does that work? I feel like I'm kind of cruising. I know I'm not really cruising, but I'm feeling good about the pace. Okay, let's go to the next. Ref counting review. So one of the great things about how we implemented our ref counting garbage collection is that the GC logic was all nicely encapsulated in the new object functions and the increment/decrement ref count functions that occur automatically within the container types. In other words, the SnekAdd function that we wrote in the last chapter will automatically handle the ref counting for us. There's no need for us to allow any of the GC logic to leak out into the rest of the code base. Okay, so It's pretty cool how a garbage collector can be implemented in a simple way that stays within the confines of the objects themselves. So is this just like literally going over what we just had? I don't, this seems out of place. Is this a little out of place? Okay, it's showing the snake add function again. To do what? So, okay, so why doesn't the snake add function need to take care of garbage collecting the resulting object? So it's because we've coded the garbage collecting object logic well. Is it just this? I think I have not understood this part actually. So one of the great things about how we implement, let me go back and look. So ref count, increment, ref count free. How much more is there here? Oh no, I don't understand. I think I've messed myself up somewhere. So is the snake add in here somewhere? No, it's not. Okay, so what are they trying to tell us? So when we do a new snake string, so we're always going to use new snake objects. So we must have that in a bunch of places, right? New snake object. So we use that every time. Okay. Interesting. You know, I think that I think I either missed when that happened or they just kind of maybe did it behind the scenes. But yeah, if we're using that new snake object every time, then yeah, that's gonna help. And then when we get rid of one, well, how many places do we do ref count deck? It's only in ref count free and then one other place, which is in snake array set. Okay. So we're gonna have to use ref count free whenever we want to get rid of one of the snake objects. And we're not really doing that yet, I don't think. Okay. 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 I'm not sure I'm fully understanding. So why doesn't the snake add function need to take care of garbage collecting the resulting object? Yeah, that we've coded the garbage collector logic to happen automatically. So do we decrement this when we add like this? We don't, do we? I'm not sure I've understood. So when we call snake add, does it actually get rid of anything? I'm not super comfortable with this one. I feel like it should really be that it's in the new object function. The new object function increments. So when we do this, it will automatically have a ref count. So snake add function, so that's not true. See, compiler does garbage collection at no. So this it can only be this, but I'm not sure I believe it. Let's move on. Okay, so chapter 11. This is the last chapter. I can hardly believe it. So, yeah, honestly, I thought I was going to be at this for longer. Well, I mean, there's still a lot in this chapter, right? There's quite a lot. Handling cycles. We built a simple reference counting garbage collector. It can handle simple types like int and float, dynamically allocated types like string, static container types like vector3, dynamic container types like array. Isn't that great? Okay, so let's take a look at this code to see what one little problem we may have in our implementation. So we have a couple of different snake arrays that each have the size 1. And look, we put the first into the second. Or no, we put the second into the first, my bad. We put the second into the first, okay. And now the second has an extra ref count. So then we remove a ref count to the first. We remove a ref count to the second. And then they should all be freed. So what is the little problem? We create a first array and shove the second array inside it. Okay. Everything here works as expected. Sure. The trouble arises when we introduce a cycle. For example, first contains second, but second also contains first. Okay, so are we going to show an example? So if we also put second into first, then we could still do the same thing to get rid of both of them, but we wouldn't necessarily know to do that. So run the code in its current state. Notice that the assertions fail, even through we decremented both the first and second array's ref counts, neither were freed. Ref count equals 0. So fix the assertions to pass by updating them to match the sad reality of our current implementation. Oh no, really? Very sad. Before I do that, let's see what it says we're observing. So the reason both ref counts are stuck at 1 after being decremented is because when first has its ref count decremented, it already had 2, so it only drops to 1. Okay, so we put second into first, and then we also put first into second, so they each contain the other. Nice. A circular reference. And then, so it only drops to 1, which does not trigger a free of the second array, and because second still has 2 ref counts, it also only drops to 1, which fails to trigger a free of the first array. In other words, we have a cycle, and our simple reference counting garbage collector can't handle it. Okay. So we really just want to say that the ref count is 1. All right, fair enough. Okay, let me hit another. Actually, I don't want to hit another potion just yet. I want to step out. Probably, maybe for the last time, because we are closer to the end. All right, I'll be back in 5 minutes. Oh, let me put up my BRB graphic. Well, it's not much of a graphic, but it's what I've got, baby. Yes. Okay, okay. All right. Let's hit it. Here we go. Gonna hit another potion. And submit. Okay. Next, pros and cons. Okay, to solve our cyclic reference issue and to force you to implement another garbage collector algorithm, ha! We're going to implement a mark and sweep garbage collector. Okay, so pros of mark and sweep can detect cycles and thus prevent memory leaks in certain cases. Less on-demand bookkeeping. Remember, all work done by the garbage collector is wasted. It doesn't make your GPT-4 wrapper? I mean, custom AI product run any faster. Reduces potential performance degradation in highly multi-threaded programs. Refcounting requires atomic updates for thread safety. Let's see. Reduces potential performance degradation in highly multi-threaded programs. Interesting. So because we do less of this, then we don't need to have as many like mutexes. We don't need to put mutexes on things as often. Is that it? I don't know if that's it. Okay. So cons of mark and sweep. More complex to implement. You'll see. More complex to implement, you'll see. So can cause stop the world pauses when lots of objects exist and must be freed, resulting in poor performance. Higher memory overhead, less predictable performance. Man, that sounds pretty messed up actually. Okay. So we'll be using a VM struct, which stands for virtual machine type. This VM simulates what would normally be tracked if snakelang were a fully functional interpreted language. It's not. This virtual machine is much simpler than a real one because all we care about is demonstrating the garbage collection aspects. You can spam Lane if you want a full write your own programming language course on boot.dev. Please don't. I have a wife and kids. Well, all right, fair enough, fair enough. So open VMH. Okay, let's take a peek. So we have frames and objects. All right, neat. We're going to need to go VM new and VM free, sure. Frames holds a stack of frames which are pushed and popped as we enter and exit new scopes. Okay, for example, scope 1, scope 2, scope 3, okay. As each of the scope entrances, in this case function calls, a new stack frame is pushed onto the frames stack. When we exit a scope, a function returns, we pop the stack frame off the frame stack. Okay. So because we use a void pointer to work with generics in C, you can't actually tell what the data type held by the stack T is for each field. We'll write some wrapper functions later to help us make sure that we don't accidentally push the wrong kinds of data into our stacks. Yay, C. I think that went over my head. Let's see here. Okay, so we're going to push a stack frame. We're going to push a stack frame. We're going to pop the stack frame when we return. And we're going to pop another one when we return. You can't actually tell what the data type held by the stack T is for each field. All the objects. Okay, okay. So the objects field is also a stack, but it holds SnekObject T pointers. It looks like stack T right now. So the stack T just has this. Let's see. So in VMC, complete the VM new function. Okay, we're gonna try and make this work. I think I got a little lost. I don't know. I feel like I was moving pretty well, but not now. Okay, so complete the VM new function. It should allocate space for a VMT struct on the heap. It should also initialize the frames stack with a capacity of 8 and the object stack with a capacity of 8 using the stack new function. Okay, so our stack new function is just we put in a capacity. Okay. All right. So we're going to say VMT star new VM equals Malloc size of, right? Okay, so we got that, I guess. Okay, so then new VM, and we point into the frames, and then we say that is going to be stack new 8. So let's see. So these are all stack. So this is, it's a stack, and the stack itself, okay, I was really lost. The stack itself holds void pointers. Okay. Okay. A void pointer to void pointers. Or whatever. A void double pointer. So it can be whatever. I was pretty lost there for a second. Okay, I think I'm catching up a little bit mentally. Okay, so new VM objects equals stack new 8. Wow, that's not at all how you spell it. And then, so stack new. Okay. So we'll return that. And then what's this next part? Complete the VM free function, sure. So if we get this passed in, then we should go free VM frames, free VM objects, and then free VM, right? Oh, remember we wrote a special stack free. Okay, that would make more sense. That would make a lot more sense. Okay. So we're going to go stack free VM frames, stack free VM objects, right? Okay. Stack frames. Think back to the warnings I gave you about working with void star data types. It's easy to push the wrong kinds of data onto our stack T because, like Starbucks Wi-Fi, it will let anything in. Okay, so pretty messed up. So to prevent us from shooting ourselves in the foot, we will create some functions that are more type safe and make it much more difficult to do the wrong thing when interacting with our VM. Wrong things like push a 7, so that's not good, or an uh-oh. Pretty messed up. Okay. I think I'm getting close to the end. I'm glad to. Okay, so but we want to make it easier on ourselves to only push frame T star types onto VM frames. So we'll write some wrapper functions to help us out. So take a look at the frame type in VM. All right. So it has a stack of references, apparently. Represent the object references in the frame. Okay. So complete the VM frame push. Sure, we'll give it a shot. So we will stack push and we'll push something onto the VM frames, and that will be the frame. Is that it? Oh, goodness. Okay. So then what does this one do? Allocate a new frame on the heap. Okay, okay. And then initialize the frame's references. Wait, I did a star there. Oh, that's crazy. This should definitely not be like that. I think I made the same mistake when I did this on the last exercise. I think I made that exact same mistake. That was crazy. Okay, so size of. And then I think I probably made that mistake several times actually. I don't know. All right, so complete the new VM new frame function in VMC. It should allocate a new frame T on the heap. Initialize the frame's references with a stack new of capacity 8. Okay, so what did I just get here? Okay, and then what's next? So we'll go VM frames, but we have to push, so it's stack push, right? Let's see if that's what it is. Stack push. Yeah, okay. And then return new frame. Okay. So then this next one, we are going to go, let's see, free the references. And is that in here? Or is that in here? Frame free. Okay. Oh no, frame free is what we're doing. Free the stack is stack free, right? Stack free is what we're talking about. So we'll go stack free frame references. Free frame. I don't know. I feel like that's not a lot. I don't know if I've missed something somewhere. Okay. Apparently it's accepted. Okay, let's see if I understand this next one better. Tracking objects. Our virtual machine needs to track every snake object that gets created. We are no longer going to track how many times an object is referenced, but instead check at garbage collection time if each object is still referenced at all. So if it is, keep it. If not, free it. So in vm.c, complete the VM track object, which adds an object to our VM object stack in a more type-safe way. Okay, so vmc, VM track object. Okay, so we have an object passed in, and we are going to go VM objects, except not really. We're going to go stack push VM objects obj. I mean, I think that's literally probably it. Let's see. We push the obj in. Do we need to, it says type safe. Do we need to check if it's null and stuff like that? Honestly, I'm not even sure. It has this remove nulls. We haven't used that yet. So add an object to our VM objects in a more type-safe way. All right, I don't know. And then, oh, so I think by a more type-safe way, they mean the fact that we have this type check. In order to pass it in, it has to be a SnekObject. Okay, so then in snake new C, update this. So now we should ensure that it's tracked by the VM. So we get a VM here, and that means that we have to use the function that we just filled in somewhere. Where are we going to use it? Right here, right? So we're going to go VM track object, and we are going to pass in the VM and the object. And that's it. Let's put it in there. All right, let's go to the next. Oh, another chest. They are so generous with these chests. Chests like crazy. All right. Love it. Okay, so recall the refcount free function that you wrote in the previous chapter. It should have looked something like this. Okay, so yeah, it was a good one. It was a good one for sure. So now we're going to say, let's rewrite our freeing logic for mark and sweep. Oh, man. Okay, this is going to be a good one. All right, so here's our stub. All this stuff has been taken out because we're going to do it differently now. So, because the virtual machine is the one tracking objects, all of the refcount deck work can be removed. Okay, so they did that. They removed all that. There's some very cool tricks coming up for mark and sweep to manage this. But for now, you can just trust me that we'll correctly free any of the contained elements if they are no longer alive. All right. So, in SnekObject C, complete the SnekObject free function. All right, so here we are. So integer, float, and string objects should all work the same as the refcount version. Non-container types. Okay, so we didn't do anything here. And in this case, we just free the data inside. Okay. Got that. Okay, so vector 3 doesn't need to do anything because the mark and sweep will handle the contained objects. Well, now we know. Array should free the elements array, but not the objects themselves because the mark and sweep will handle that. Well, that makes it so simple, at least in this file. My goodness. So we'll free the object data v array elements. And okay, so that's cool. So now in the VM free, what do we have to do? Iterate over all the VM frames and free them using frame free. This one is a difficulty 9, so let's not get too cocky. Yeah, so iterate over all the VM's frames. So if we look again, the VM frames are just this stack. And when we want to iterate over the stack, actually, when we iterate over the stack, do we stack pop or what do we do? The stack pop doesn't like actually return anything, right? So I think we just want to go over the actual data in the stack, I believe. Oh no, this does return something. What am I saying? It returns a void star. Okay, so we just want to pop until everything is gone. And when we do stack pop, it'll be null. Okay. So we'll just go while stack pop is not null. Right? Okay. So it's going to be and then the frame itself, what is the frame itself? frames like this, but when we add a frame, it should be a frame t. Okay, so frame t star frame equals VM frame, or actually stack pop VM frames, right? So then we say while frame is not null. Okay. Frame free frame. Frame equals stack pop VM frames. Iterate over all the VM's objects and free them using SnekObject free. Okay. So, wait. When we put the object on, what is it? It's a SnekObject T. Okay. So we'll go SnekObject T obj equals stack pop VM objects, right? And then we'll totally just go while obj is not null. And then we'll go SnekObject free obj. And then we'll go obj equals stack pop VM objects. Sure. And then let's see. So I didn't do stack free yet. So we're gonna go stack free VM frames. And then we're gonna go stack free VM objects. And then we're gonna go free VM. Okay, I feel like I could benefit from potentially going over some of this stuff again. I'm starting to get more than I did before, I think. Okay, let's go to the next. Frame references. Consider this example of snake-laying scopes and stack frames. Okay, so in scope 2, we add message 2 to its referenced objects. Okay. Once again, this is a bit simplified from what you would do in a real production-grade language, but the idea is the same. Well, good to know. So each stack frame needs to know about all of the objects that it references. Okay, looks like this is an easy one. Difficulty 4. So all we're going to do here is we're going to go stack push obj frames, right? Nope. No member named frames. Oh, it should be VM. Okay, so where, wait a minute. Should push the object onto the stack of references for the current frame. Okay. I'm way wrong, way wrong. Oh my gosh, oh my gosh. So it is stack push, but we're looking at frame references, which is exactly what it says. I don't know, total brain fart. Okay, let's go to the next. Mark and sweep. So we finally have enough machinery in place to start thinking about the mark and sweep part of our garbage collector. So what is the algorithm? Mark and sweep garbage collection was first described by John McCarthy in 1960, primarily for managing memory in Lisp. It's a two-phase algorithm. One is the mark phase. In the mark phase, we traverse the object graph, marking all reachable objects. Fun. In the sweep phase, we scan memory, collecting all unmarked objects, which are considered garbage. Amazing. Very cool. So note. We don't keep track of how many times a particular object is referenced like we did with reference counting. Okay? Instead, We keep track of which objects are referenced in each stack frame and then traverse our container objects looking for any other referenced objects. That's what traverse the object graph means. A fancy way of saying look for objects. Okay, cool. So in SnekObject.h, in SnekObject.h, add an isMarked, oh, wow, I was reading that really wrong. Add an isMarked Boolean to our SnekObject.t struct. Okay, cool. Okay, so here is our struct. Wait, where is it? Here it is. Okay, so we're going to say bool isMarked. Okay. And then in here, we're going to say isMarked is set to false when we create a new Snek object. So we're going to say object isMarked. Okay, is that all we need? No. Okay, so far so good. To do, would it be funny to just have a video clip of me going mark and that's it? I'd advise against it. All right, so in some mark and sweep implementations, you'll see different ways to mark root objects, the objects directly referenced by stack frames. However, in our simplistic VM, it's a bit easier to find and mark all of the directly referenced objects. You'll see why when you write it in a moment. So we're going to complete the mark function. Here we go. It should set every object that's directly referenced by a stack frame to isMarked equals true. Okay, so we're going to iterate over each frame, but this time we don't want to pop them, right? So let me take a look again. We want to leave them where they are, I believe. So this time I don't think I'm going to try to pop them all. I think I am just going to loop over with a regular 3-clause for loop, right? Because we want to leave them on the stack where they are, I believe. Okay, so the VM has these frames, and then the frames have these references. Okay. So we're going to go for I equals 0, I is less than VM, and it says how many are on there, right? The count. VM frames count, right? I plus plus. And then we'll go for int j equals 0. J is less than VM frames. And then we're going to have to go into the data, right? I guess that's how I'm going to do it. I don't know if this is the best way to do it. Data sub I. And then that itself should have a frame which has references, and then the references should have a count. Oh wait, the data, yeah, I think this is okay. VM frames count. The frames itself is a pointer. So do we have to go like this? And what about the data? The data itself is a pointer as well, right? Frames, data sub I, references, count, j++. I think I got a little lost somewhere, but we'll see if this is okay. So then we're going to say VM frames data sub I references data sub j isMarked equals true. So yeah, so the data itself, we think should be referencing an object. Okay, let's see. I think I've screwed that up. That seems convoluted. Okay, not a structure or union. Okay, the compiler is gonna help me untangle this knot that I've created here. I think. We're gonna see. So it says reference base type void is not a structure or union. Okay, makes sense to me. So we need this to be, I guess, cast to what we think it is, which we think it should be a frame, right? So this will be frame t star, and that is what we think this part should be. Okay, is that any different? So yes, that is. So then we are going to do the same thing here. Frame t, and then presumably we need to do it again for the references data, but let me just see what it says here. Amazing. Okay, so then this is going, oh god, this is crazy. So this is going to be SnekObject t star, and that's here. Okay, yeah, that is spaghetti. That is spaghetti like crazy. I'm just gonna move on. That is spaghetti like crazy. There's just a few left, so I'm gonna hit another potion and oh, it's actually just 2 left. Amazing. That is spaghetti like crazy. Oh my goodness gracious. Actually, you know what? I said I was gonna move on, but should I fix this spaghetti? Honestly, probably yes. Let me just fix this spaghetti real quick then. So what it should be is it should be more like we're gonna, so what are we even looking for? We're looking for a frame. So we're gonna say frame t frame equals frame t star vm frames data sub I, right? And then we're gonna remove this spaghetti, right? And it's just going to be frame. Okay, so much better. And then here, we're going to go SnekObject t star obj equals SnekObject t star. So technically, I mean, it's more to type, but that spaghetti was wild. Okay, so SnekObject t, and then we're going to go frame, and we're going to go references. No. Frame references data sub j. Okay? And then we're going to get rid of, like, pretty much everything. Get rid of all that, and this is just going to be obj. Ah, see, isn't that much less spaghetti-ish? Let's see if it still works, though. Yeah, that's more effing like it. Phew, okay, that's way less spaghetti-ish. All right, let's go to the next. Okay, so trace. So now that we've done the first and simplest part, marking. Okay, well, he's hyping something up. Sweep, is sweep going to be the tough one? We'll see, we'll see. This one's only difficulty 6, so I don't know if it should be hyped up like this. So we've done the first and simplest part, marking. We can trace through all of our objects and determine which ones are connected to the roots. For example, if we have a get list and we set an A and then we return a list with an A in it, and then we print get list, okay. So if we run this code, it will return a list with the integer A inside of it. So far, so good. Our current mark function will mark the list, but it won't mark the integer A, which means that when we go to sweep the memory, we will mark the list, but not the integer A. Okay, sure. We then free A while it's still being used. Oh, okay, gotcha. And the operating system could then fill that memory with something else, which would be very bad. So we need to prevent this. But we also have another problem. In the above very dumb example, so we create a list, and then we put it into itself, and then we return and then we return an unrelated list. Okay, so sure, very dumb. Okay, so we create a list, we put the list into itself, and then we return an unrelated list. So we create a list that references itself and then return a completely unrelated list. If our trace function looks for any object that is referenced by any other object, it will consider A alive because it has a reference, albeit to itself in this case. So in fact, A is unreachable because when getList returns, A is no longer used anymore. So tracing solves these problems. To be clear, tracing is part of the mark phase of mark and sweep. It's where we mark all the objects referenced by our root objects. This is one of the larger assignments. Take your time. You're almost done with the course. It's only marked as difficulty 6. Okay, well, it's hyped up, so we'll see what it is. Okay, so it looks like we have 3 functions to complete. So we're going to start with the bottom one. Trace mark object. Okay, so for trace mark object, we're going to say if obj is null or obj is marked, then return gray objects stack. Okay, so then we will say obj is marked equals 1, and then we'll say stack push. Okay, stack push gray objects obj. Amazing. So that's cool. So then what else can we do here? That's it for that one, right? So now we'll go to the next one. And for this one, we are going to say if it's an integer, float, or string, do nothing. Okay, so let's do a little bit of a switch here. We will switch on ref kind. Okay, so case integer, case float, case string, break. Case vector 3, we will say trace mark object, gray objects, and then we'll put ref data v vector 3 x, right? And then we'll go okay, like that. Okay, break. Okay, so what about case array, right? Array is the other one. Called trace mark on each element. Okay, so makes sense. Okay. So tracing, okay. Starting to make a little more sense. So we're going to go for I is less than ref data v array size. And then we're going to go trace mark object. Wait a minute. Why did I do it like that? What the heck? That was weird. Okay. Gray objects. And then this one is ref data v array elements sub and then break. Okay, so that's good there, I guess. So then what is the trace? Create a new stack. Okay, so we're going to say stack t array objects equals stack new 8. Sure. If array objects is null, return. Okay, sure. Iterate over each of the objects in the VM. So we're gonna go for int I equals 0, I less than VM objects count. Right? Plus plus, sure. And then we're gonna go if VM objects data sub I. But here, let's do the same simple little trick to avoid being spaghetti-ish. So we're just gonna say snake object equals objects data I, right? Oh, I didn't put the name. Obj. There we go. So if obj is marked stack push gray objects obj. Okay. So then we're going to say snake object t gray object equals gray object, or no, excuse me, stack pop gray objects while gray object not equal null. We are going to say I feel like this is getting like slowing quite a bit, or like my computer is slowing down. Just the website, I think. I'm gonna refresh it after I submit this one, probably. Oh, I still need another XP potion. All right. Okay, so while gray object is not null, we're gonna say trace blacken object gray objects gray obj, and then we're going to say gray obj equals stack pop gray objects, and then free. Oh, no, stack free, stack free gray objects. I think that works, so I'm going to hit my potion. I'm going to submit. Okay, I'm going to go ahead and refresh my page because I think it's not fast. Okay. I don't know if that makes any difference, but let's just see. So this is the last one. I feel like it makes a difference. This is the final required lesson for this course. Okay. So sweep is easy. He says sweep is easy. Here it is, difficulty 10. All right, sweep is easy. Trace was probably the hardest part of the garbage collector. Every object now has an is-marked field that we can use to determine if an object is reachable or not. All we need to do is iterate over all the objects in the VM and free any object that is not marked. Once it's freed, we can also remove it from our VM. Oh, and one more thing that's not obvious about sweep. Any object that is marked, we don't want to free it right now, needs to be reset to isMarked equals false. That way, the next time the mark phase runs, if it's not marked again, it will be freed in the next cycle. Okay, cool. All right, so we've got sweep and we've got VM collect garbage. Hope you liked the course. Great work. Don't say it prematurely. We still have to finish this final lesson. Difficulty 10. All right, let's see what we're going to do here. So let's start with the sweep. So iterate over all of the VM's objects. Okay, so we're going to go again for int I equals 0, I less than VM objects count I plus plus. Then we're going to say SnekObject star obj equals VM objects, and it's data again, right? I've done this so many times already. Data. Okay. Data. I'm a little fried, but not too bad. Iterate over all of the VM's objects. So if the object is marked, reset is marked equals false and continue. Okay, so if object is marked, object is marked equals 0, else free, or no. Wait, what do we use for the free? It's the SnekObject free, right? SnekObject free obj. Okay. Set the data at that position in the stack to null. Okay, sure. So we're going to say VM objects data sub I equals null. Okay. All right, so then once we're done with the loop, we will say stack remove nulls VM objects. Okay. Is that the whole sweep? All right, not too shabby. This is the function that runs the GC. Okay, so this is a difficulty 10. I'm worried. Mark. Okay, so mark needs to take the VM. Trace also takes the VM, I think. Yep. And sweep takes the VM. Okay. And it looks like it worked. And we've got the potion ready, so that's it. You've completed the Learn Memory Management course. Claim 5,000 XP. Love it. Okay. Well, that was a good sesh here. I don't really want to do anything else today. I'm feeling good, though. I think that was a great, great course. I think it was awesome. And, of course, that puts me back at #1 on the leaderboard. And check it out. If there were more XP to get, I could become the first player to reach level 150, right? Like, it's almost within reach, but there's hardly any